Om Namah Shivaya. A very pleasant good evening to everyone. I am Dr. P. Kannan, Head of the Department of Electronics and Communication Engineering, and it gives me great pleasure to welcome you all to day 5 of the AICTE sponsored ATAL online 6-day faculty development program on semiconductor for smart systems, applications in IoT, artificial intelligence, and next generation devices, organized by the Department of ECE in association with IQAC and IIC Sri Satyam College of Engineering and Technology. The theme for today's sessions is AI and semiconductor fabrication for edge and smart devices, focusing on cutting-edge trends in neuromorphic computing, on-chip AI, and semiconductor fabrication for next-generation systems. We are honored to have two distinguished experts with us this evening who will guide us through these advanced topics. Let us begin with technical session 9. To formally introduce our distinguished expert for technical session 9, may I now invite Professor C. Sasikumar, Head of the Department of Computer Science Engineering, to introduce the resource person.
It's given me immense pleasure to introduce our esteemed expert, Professor in the School of Electronics and Engineering at VIT Chennai, Dr. A. Anita Angeline. Dr. Anita Angeline holds a PhD in high-speed processor variation tolerance, VLSI design, and possesses more than 2 decades of rich teaching and research experience. She has guided numerous BTech and MTech projects in electronics and VLSI design, many of which have led to quality publications. Her area expertise include high dynamic logical circuits, low power arithmetic design, neuromorphic concepts, hardware software products, partitioning, and process variation tolerance circuits. She has been an active reviewer of computer journals and has contributed the academic community through her work in custom and semi-custom IC design using advanced EDA tools. We are truly privileged to have such an accomplished academicians and researchers with us this evening to share her insights on chip AI, edge computing using neuromorphic and in-memory semiconductor that beautifully bridges hardware intelligence and next-generation computing paradigms. Madam, we warmly welcome you and look forward to your
So thank you, sir, for the warm and detailed introduction of our expert. Now, with great pleasure, I invite Dr. Anita Angeline ma'am to deliver her session on neuromorphic and in-memory semiconductor design for edge AI. Madam, the session is yours.
Thank you, Professor. Thank you, Professor, for your nice introduction. I'll share my screen. A warm good evening to every one of you being assembled over here. It gives me immense pleasure, and I consider it as a big privilege for giving my insight on the neuromorphic. So basically, my expertise is on the process variation tolerance, high-speed dynamic logic designs. And now a little bit we have explored into this on-chip AI. So whatever the knowledge we had acquired, maybe in this evening, I'll just share you whatever we have acquired. So this is basically an interesting topic, on-chip AI. So probably in the next 1.5 hours, we'll just go through what are the avenues, what we are having on this area, what are the basics we need to know, and what is the expectation or what is the result we come across with this thing. Okay. So on-chip AI, edge computing using neuromorphic and in-memory. So the title itself conveys what is this on-chip AI? It's edge computing. So whenever we want to deploy any artificial intelligence method on the edge, basically in the application, we go for implementing using this VLSI chips. So for today's evening, these are the topics, these are contents. So initially, I'll be a little bit elaborating about what is this edge computing. And when you see about this edge computing, it is basically the implementation of the deep learning or the machine learning methods in edge itself. Now, before 2-3 years, we had the terminology cloud computing in a wide manner. It was prevalently used. But now, when you go for the cloud, what is the difference it makes in this age? That is the first thing what we are going to learn here. And considering that, how do you go for this neuromorphic computing? Because whenever you are going to use the deep learning and machine learning methods, how the brain inspired algorithms could favor better. And based on that, we are going to more dive into the spiking neural network, which is basically a subset of the neuromorphic computing, and how this spiking neural network could be implemented as a chip. Because our focus for today's evening is on-chip AI, right? So ultimately, when you say about the spiking neural network, it needs to be implemented on the chip. So a little bit, I'll just give an insight about how it's being implemented and what are the elements we are going to use, how it is going to be applicable, etc. And the next thing I'll be just a little bit elaborate about what are the research paradigms based on this, because this is a very niche area which is an upcoming field. So a little bit I'll elaborate on what are the research avenues or research diversities which are possible under this particular neuromorphic computing. Now, going on, what is this on-chip AI? Now, the very name says it is AI at the edge with hardware acceleration. Now, we all had come across many times about artificial intelligence. Okay, the intelligence. Now, whenever we say about this intelligence, as I've been saying, cloud computing plays a vital role. Whenever we say about the cloud computing, it's very well known. We need a particular platform for it. And nowadays, we have the TPUs into existence basically. But when you say about the cloud computing, it deals about the acquisition of the data from the particular application, transmitting to the cloud. Then in the cloud, the particular intelligence is being applied, and based on that, a decision is being taken. So now, what actually happens over here when you go for the cloud computing is lots of what I can say, the latency involved is much more actually. So that is a main drawback what we have in this AI. But in the case of on-chip AI, the entire AI computation we are trying to integrate into this hardware. So you might be wondering, what is this hardware? So now, maybe before 2-3 years, the hardware what we were dependent on is about the Arduino, RPA, etc. But nowadays, this hardware is more focused towards SoC, FPGAs, ASIC, and exclusive neuromorphic chips. Now, as I said, the first thing is about cloud computing. The drawback is more of the latency involved over there. To get rid of that, we try to build the intelligence in various edge device, a hardware device, something like Arduino. But if you're going to use that, it may not be a power efficient one, or it may not be producing a particular result as we expect. So in that case, we go for designing the chip. So these are the three steps what had made this on-chip AI to be realizable. The cloud computing, then came the edge computing with the various processors, something like Arduino R5. Then came the hardware, our exclusive ICs, SoCs or FPGA or ASIC. Okay. So basically, when we speak about this on-chip AI, it enables the local intelligence without relying heavily on the cloud. That's what I said. It's not going to be a cloud computing anymore. It is deploying the intelligence at the edge exclusively on an ASIC or a neuromorphic chip. And the problem what we have in the case of a cloud computing is more of latency. That is being get rid. So we are able to perform very good real-time processing within fraction of second and with a greater accuracy also. And another thing, when we go for these sort of hardware, something like an ASIC or a neuromorphic chip, the energy efficiency is much good while compared to that of any microcontroller. So that is a major advantage what we have in the case of an on-chip AI, while compared with that of any other general purpose microprocessor or microcontroller that we have. And above all, what happens is the security involved is also found to be much more actually, because when you transmit to the cloud, that there are lots of breaches wherein your data may be stolen. But that is not possible if you're going to use an application-specific IC at the particular edge. So the security is also good, and also in addition to that, because of the local data processing, there is less cloud transfer. Okay, so we are not dumping the cloud anymore with lots of big data being available. So that is what is on-chip AI. So to say it in a nutshell, the intelligence method is going to be implemented in the application itself. wherever you're going to have the application, it is being implemented. So ultimately, it results in a faster operation, instant operation, basically, we can say. And apart from that, it offers a good energy efficiency and also good security. So this is what is on-chip AI. So when you say about this on-chip AI architectures, basically the major category could be of two types. First one, we call it as AI accelerators. The second thing, we call it as a neuromorphic processors. Maybe in the latest slide, we'll get to better know about what are these accelerators and what are these processors. Now, for example, I think all of you must have known about the tensor processing unit. So when you see about the tensor processing unit, it is a Google product and it's basically an ASIC. So the main focus here is how do we accelerate the operation. Now, as we all very well know, as we come to the generation of the computers, initially you must have heard about dual core, quad core, like that. The architecture itself was being given in a, what I can say, in an advanced measure, so that the speed of operation is found to be much more actually. So now this TP is nothing. It is an accelerator where we have the intelligence also being possible, and it is realized as an IC over here. So that is about the first category, which we call it as a AA accelerators, or also we refer it as a hardware accelerator. Coming to the second one, it's called as a neuromorphic processor, which is what we are going to deal it in an extended manner. Here, we are much bothered about however our brain is working, we are going to do the processing. So rather than having the computation being done in terms of zeros and ones, here only it is going to be an event-driven one. So the advantage, it's something like, however our brain, if there is a trigger, accordingly your brain is functioning, the neuron is functioning. So mimicking the neuron, we're just going to see about how the processing to be done. So that is what is being given by this Lohi by Intel, and also True North by the neuromorphic processor, by the IBM. And there are also certain FPGA-based AI designs. Because as we are very much aware, when you go for an on-chip AI, if you're going for a semi-custom design mode of approach, initially we will try our trials using FPGA, and I'm getting a better, what I can say, better expected results. We'll go for an ASIC deployment. So this is how the on-chip AI architectures are being developed. So as I've been telling, the TPUs, IBM True North, they are found to be widely used, and they have proved that rather than going for a conventional GPU, this is found to be much more good in terms of the particular edge application. Now, as it's been saying about the application, because repeatedly I'm saying it is on edge, with respect to an application, we're going to have the processor being built. So basically, what we are having in our day-to-day life, your face ID recognition in your mobile phones, or your voice recognition, what we have it in Alexa, Siri. Then we have the autonomous vehicles nowadays. So when I say about the autonomous vehicles, there is a need for the real-time perceptron. If I have to see, there are two aspects what had to be looked at, whether there is an object blocking obstacle direction, and also it has to take a decision on how it has to turn, whether it is to the left or the right, etc. So these sort of things are also expecting a particular intelligence to be deployed in the chip. And coming to the third sector is the healthcare sector, where we have the wearables. It may be for a disabled person, or it may be for a regular checkup, or it may be with respect to the telemetry, or whatever may be the scenario. When we come to the healthcare sector also, certain times, if there is an abnormality in a particular person, the data could be acquired, and based on that, some decision could be acquired. So for all these sort of things, we require an on-chip AI. Another example, what we have is the IoT edge devices. Maybe a smart home where you can automate your doors, your cooking process, you can have the surveillance, who is opening the door, or whether any abnormality, if anything is being switched on, and incidentally, all these sort of applications require some intelligence to be applied. So when I say about the intelligence to be applied, in the earlier days, it was only made feasible with the help of the cloud computing. But now, as you see, as the generation of your processor is going on, your processor itself is capable of doing. That is what we are going to learn this evening. That is, your chip, the processor, what you are having is applied with some intelligence, so that it is able to perform in a smarter manner, we can say. Now, as I said, when I say about making your architecture, okay, making your processor to be efficiently working, again, as I said, there are two aspects. One is you could improve your architecture, okay, maybe by means of parallel mechanism, pipelining, etc. Another way is how the processing is being done. That also is one way by which you could deploy your intelligence on the chip. So as I said, these are the certain architectures where we have the TPUs, NPU, Lohi, etc. And these are the various applications that we go for. Now, considering this, what are the challenges we are having? Because we said with respect to an application on an edge, we have to cater to designing a chip, right? So in that case, the first problem what we encounter is the hardware cost and design complexity. Because when you see about the neuromorphic or the on-chip AI, there are lots of challenges involved in the design. When you see about the design, if you go for a neuromorphic computing, I have to mimic the brain. So how it functions, what is the spiking rate, or what is the refractivity, with the frequency of how much it is supposed to get back and again go for identifying a new object. All these design complexities are involved. Because why I call these as design complexities means we have to design the chip. If I go for a custom design, the transistor sizing has to be done accordingly. But when I go for a ASIC design, I have to ensure that I don't have any timing violation, function violation, or anything. So these design complexities have to be much more when you go for this sort of on-chip layout. And the hardware cost is also going to be a huge one. And coming to the second challenge, what we face is with respect to the scalability of the AI models. Now, the general trend, what we have as of now is, we are not going to, because as you are very much aware, when you say about a neural network, it involves two phases, right? One is your training, one is the testing phase. So on training, we acquire the weight values, the bias values. That value needs to be dumped into your chip, right? So when I'm training it, here if I'm going for any Anaconda or Jupyter platform, I may be getting some weight values. It may be a floating point representation or a fixed point representation. The same weight value needs to be transformed into my chip. So when I'm working with the chip, for example, if it is a semi-custom design, if I have to implement a MAC architecture, I may be having an input value of 8-bit processing ever done. But on my AI model generated, I would obtain the weight value as a 16-bit value. So what I need to do is I have to go for scaling it. I have to go for quantization. I have to go for truncation or something like that, so that I have to fit in my trained weights as well as bias in my on-chip. So the scalability is one huge challenge which we come across in this on-chip AI. And the third one is related with the updating and the retraining models on the edge devices. Because, as I said, if you're going to train it with a conventional platform, something like Anaconda or something, here on updating, you may be having a different weight being generated. So this weight value again needs to be dumped in your on chip. So the retraining timing or the updation has to be done instantly. So it takes some timing, it takes a procedure to be done, because in most of the cases they have a particular framework for doing it. So all these things become a challenge. And very importantly, as an IC designer, balancing the performance and the power consumption also becomes a huge challenge, as we are very much aware. As the speed as well as the power consumption, we are going to have a huge problem. So these are the trends what we are having on designing an on-chip AI. So when you say about designing an on-chip AI, it's ultimately designing an IC to implement the intelligence, right? So for implementing the intelligence, I have to have a training algorithm wherein I take my trained weight value and the bias value, put it on the particular chip actually. So ultimately, this transformation itself is a huge task, and it requires more time and more procedures to be done. And also certain, what I can say, some algorithmic changes also need to be done with respect to the bias in weight values, etc., so that you'll be able to run it as an on-chip AI mission. Now, again, if we say about the challenges with respect to the other thing, the first thing is about the integration with the 5G or the 6G network. So the frequency of operation in which you're going to operate, that balancing also, the synchronization also becomes a little bit a problem. And apart from that, the growth of TinyML. Now, most of us would have worked with the TinyML in a microcontroller very easy manner. So basically, that is also one advantageous way of how we could go for it. But only problem what we have while we are using TinyML is the processor is not a customized one. But whereas if you go for an on-chip AI or designing an ASIC or a neuromorphic processor for your application, it could be more compact. It could be made very much power efficient also. And then apart from that, the hybrid edge cloud intelligence, which I was saying, that is in the cloud mode, you are acquiring the bias and the weight value. Ultimately, it has to be transformed to an appropriate representation in your on-chip. So that is also a huge challenge. And coming to the next one, it's about the brain in square neuromorphic computing. So these are certain challenges what we come across when you're going to implement this neuromorphic computing. So what we start with, because as I said, there is a differentiation. We have to know about what is this hardware accelerators as well as a neuromorphic processor. So now, as you're very much aware, what is this artificial intelligence? The science and the engineering of creating intelligent machines. So the thing is, rather than each and every time we are suggesting or we are giving instruction, we are creating some intelligent machines. So when you say about the machine learning, it is a subset of this one, that which makes our computers to be able to learn without being explicitly programmed. Okay, because I think in the case of an artificial intelligence, we write some fuzzy rules or sort of thing, but here in machine learning, we just give the features. If the features is according to that, accordingly a particular decision will be taken. And coming to the subset, which is a brain expert, which is of more importance of today's evening, it is about the algorithm that takes its basic functionality from understanding how the brain operates, our brain. So when I say about our brain, we have the neurons, which is the main thing for acquiring the signals and making a decision based on that. So however, our brain inspired neurons, that is our brain neurons are working, we are going to make our chip to work. So that is called as a brain inspired computing. So when you say about this brain inspired computing, spiking is a very important thing what we have to know. Now, what is it spiking? What is the difference it makes? As I have been telling earlier, we are not just going to continuously process the information. The information will be processed only if there is an event occurring. Okay, whenever there is a spike being generated, the entire operation will be happening. So the particular neural network, it just waits for an event to be triggered, and based on the event, it just goes for triggering it. And now another aspect, because nowadays we are having, where I think deep learning is another subset with respect to the big data being available in huge chunks, we go for this deep learning where we don't need, where human interference is very much reduced actually. So this is also one subset with respect to the big data, or what I can say the data set being available, the machine itself is able to learn and make appropriate decision. So now the regime of today's era is, we can go for brain inspired spiking neural network design, wherein your energy consumption is very less. That is one aspect. Another aspect is, when you're working with a big data, what we could do is we can go for implementing these deep learning methods in the chip. Okay, so both the things what I have been telling is what we are going to implement the architecture as a chip. So one category could be the spiking neural network, where it's basically a brain inspired one. Coming to the second category is with respect to the lots of data set available, your machine is able to, or your chip is going to do the job of creating the intelligence. Okay, because when we give a particular data set, it's able to train itself, and depending upon the weight value and the bias value occurred, when the next time when you're going to give the data set, it is able to predict what type of image or what type of character, etc. So these are the two aspects. One thing I can say in a nutshell is the spiking neural network, which is basically a brain inspired, and it's a brain mimicking also, I can say, because only if the event rises, when the event is spiking, it is able to deliver. Another category is about the deep learning, where it involves huge chunk of data. So you need to have the architecture being chiseled in such a way you are able to have an optimized performance in your on-chip AI. So with respect to that, as I said, the second technique is about the hardware acceleration, where you have the big data availability. And as I said, when I say about the big data availability, for example, the images what we are uploading in the Facebook, or the YouTube videos what we are uploading, the Walmart, the customer data, how much they are going to procure, etc. All these things are available in the net. Okay, being in the cloud. So by using of machine learning techniques, it is processed. For example, in the case of a Walmart, depending upon the customer, how much they are getting, or in what season, what day, what type of fruits they are buying, all that records is being taken into account, and based on that, the decision is being taken. So based on the data set which is occurred, lots of chunks of data being available in the cloud. So we need very good ML techniques to segregate the data, which means we require huge processing to be done. When there is a need for a huge processing, we need to have GPU acceleration. So this is one aspect of how the deep learning, the brain-inspired deep learning, could be enhanced with respect to the hardware. Our concern for this evening is basically about the brain-inspired spiking neural network. Okay. Now, going as I said, this is a hardware accelerator. So now, what is this neuromorphic computing? So when we say about this neuromorphic computing, they are basically brain-inspired AI systems, brain-inspired artificial system. What it means is, however our brain is going to work, we are going to make our chip also to function. Okay, for example, if as our brain is processing, for example, on seeing a cat image, we are able to understand if it is having 4 legs, etc. One time, someone else, or what I can say, we get a knowledge about if this is the scenario, this is the object, this is the animal. Similarly, our on-chip AI, the neuromorphic processor, is going to be trained in that aspect, and automatically the next time, whenever a similar data is being given, it finds out what type of character it is. So basically, when I say about this neuromorphic computing, it is a brain-inspired AI system. It bridges the neuroscience and the artificial intelligence. Or in another way, what we can say is it's mimicking our mimicking the brain and applying to that of a developing a chip. So here, basically, it is the hardware and the software system which are inspired by the human brain, and it mimics the biological neural networks for efficient computation. And as I've been repeatedly telling, it is a spike-based signaling. Okay, so what is a spike-based signaling is only when there is an event occurring, the processing is going to happen. It's not going to be in a continuous fashion. So from that itself, we can understand it will consume only less power. So here, in the case of a neuromorphic computing, as a conventional brain, neurons are going to function. Whenever an event is triggered, for example, if let us assume we have we are pinching someone. So when you are pinching, only the event is triggered, right? So that goes to your brain, and depending upon that, the reflex action is happening. The same way, what actually happens over here is, as the event is triggered, it may be an image recognition system, or it may be a video recognition system. So whenever there is a change in the input, automatically the processing will be done, and based on that, the output is going to come. So now, when I say about these neurons, it is capable of acquiring the information, and based on that, if it is what I can say eligible, or if it is a good fidelity signal, then it will be transmitted to the next neuron. Likewise, it is communicated. So that is what is the synapse. So first, we have the neurons doing using the dendrites and the axons. We capture the particular stimuli, and if it is a valid one, it is communicated by means of the synapses to that of the next neuron, and it is a spike basically. So these are the 3 concepts what we have to be very much aware when you go for this spiking neural networks. So the first one is about the neurons. Second one is about transmission of this input stimuli to the other neuron using the synapse. The third one is all these are event triggered, and they are basically spike. It's not continuous zeros and ones. Repeatedly, I'm telling this. It's just a spike. So this is the first thing what we have to remember when you go for the neuromorphic computing. Coming to the second one, it is a traditional computing. The von Neumann is quite different from this neuromorphic process. So what is this we are going to do here is, in the case of the neuromorphic computing, we are having an in-memory computing, I can say. Because in the case of, probably it's like, in the case of a von Neumann architecture, what happens, we'll have a CPU and we have a memory. So generally what happens is, since if it is a neural network, as I've been telling, the weight values and the bias values are captured and they're stored in a memory. So on processing a particular neural network, each and every time, your weight value and bias value are going to be fetched from the memory. So this involves a lots of latency. And here the drawback what we have is, maybe parallel processing we may not be able to provide, as well as the scalability is also not possible when you go for the sort of von Neumann architecture. But in the case of a neuromorphic architecture, it is just going to simulate as a brain actually. So which means The computing is done inherent with the architecture. Okay, so that is the specialty what we have in this neuromorphic. So the second thing I want to stress on here is, first one is about it is a spike-based processing. The second thing is it's about the computing, in-memory computing. We are not going to have a one-even architecture. In most of the cases, if it is a brain-inspired computing unit, it's going to be a in-memory computing. So that is the second thing. So the figure very clearly shows here, in the case of a one-human architecture, the first difference you can see here, I have a binary input being given and a binary output is provided, which means some zeros and ones for a certain duration of time. But when you say about this neuromorphic architecture, it's not going to be zeros and ones, only on triggering an event by means of a spike. So when you see about the spike, generally it's defined with a particular threshold value, because we cannot say the spike will be going some threshold. If we are working with the 180 nanometer technology, maybe around 500 millivolts, if it is going to generate a voltage, we call that as a spike above the threshold voltage. So that is what the spike input, some triggering for a few moments of time. So that is being provided as an input instead of a binary input in the case of a neuromorphic. The second difference, as I said, the computing is not going to be the conventional memory as we have the volume, it is with the in-memory computing, or in other words, we call it on-chip computing also we call it as. That is the second specialty what we have with respect to this neuromorphic architecture. Now, as you can see here, the output which is being generated is also found to be a spike out, because in the conventional things, we have the binary output being coming out. But here we are just going to have the spike output being here. So these are the traditional differences. So this is the main difference what I would like to highlight over here. So if you say about this spiking neural network, which is a subset of this neuromorphic computing, we can call this as a third generation ANN. Okay. Now, what is the first generation ANN? Because in the first generation of ANN, if the value is either 0 or 1, a particular action is being taken. Okay, if I say about this particular thing, it's something with prevalent to the neurons. So various inputs are being given, and these inputs are multiplied with the weight values and added with the bias values. And on acquiring the accumulated things, if it is exceeding zeros or ones, accordingly an appropriate action will be taken. But when you come to the second generation, ranging from 0 to 1, the values are considered. That is about the second generation. The third generation is one what we are speaking now is about the spiking neural network, wherein on triggering a particular spike above the threshold value, accordingly a particular operation. So this is the biological neuron. It's going to have the axons and the dendrites. Based on acquiring the signal through the dendrites to the axon, if it is exceeding a particular threshold value through the synapse, it will be connected to the next neuron. This is the general understanding of a biological neuron. The same implementation is done in the case of the spiking neuron also. So as you can see here it is just a binary, either zeros or ones, depending upon the decision is going to be taken. Here, ranging from 0 to 1, the artificial neuron is deciding. But in the case of a spiking neuron, for a fraction of time, depending upon the particular thing, the inputs and operation is done. The second row, what you can see here, represents this thing. Only when the spike occurs, the processing is going to happen, and the condition, the constraint over here is the spikes has to be above a threshold voltage. So now, as we have the conventional neural network architecture, we have this spiking neural network architecture, which could be depicted in this manner. Whereas the first generation, the good example is the MLP, what you can see over here. Now, so to coming from this, what we understand is, when we say about the human brain, the main thing is it's massively parallel and energy efficient operation to be done. And in the similar fashion, the neuromorphic computing is also bridging the gap actually. So here, as I said, it's a spike-based computation what we're having. And the very much advantage what we have over here is about the parallel and the distributed architecture what we are having. And the energy efficiency is quite good actually. So why the energy efficiency is good is, with just only the event is arriving, when the particular spike is generated because of the input triggering, it is going to process information. So generally, the power consumed is going to be very much reduced when you go for these sort of spiking neural network. And similarly, as I said, the previous point is about the parallel and the distributed architecture. So now if you see here, it's basically, if you consider the first layer of neuron, all things could be going in a parallel fashion and depending upon the weight value as well as the bias value stored here. Now again, as I said, it's an in-memory computing in most of the cases. So in that case, all these operations could be going on in a parallel and also in a distributed manner, which will make the entire operation to be faster while compared with any other sort of KNNs over here. So these are the main advantages, and very importantly, it's about the heavy mechanism. There is a learning is basically by means of this yesterday, which we call it the spike timing dependent plasticity. So, as I said, when I say about this neuromorphic computing, the subset SNNs, the spiking neural network, it is a third generation SNN and it has various advantages. Now, to start with, it's about the biological and artificial neuron. So, very much we were known about the structure of a biological neuron with the cell body, the dendrites. So generally the information is acquired through the dendrites, and on reaching the cell body, they are being accumulated. And if it is exceeding a particular voltage, which we call it as a membrane voltage, that information will be conveyed through the synapse to the next neuron. So this is the biological neuron. So generally in our brain, we are having around 86 billion neurons in the brain, and we have around 10 power 14 to 10 power 15 synapses over here. So here the signals are being received with the dendrites and it is transmitted to the other one, these are the synapses. Now, when this is going to be transformed into an artificial neuron, because what we are going to try to implement is this, it has to be an semi-custom RTL design, or it has to be made as a custom designer circuit. In that case, we are having some input values being given, which is multiplied with a weight value and then accumulated because it's a MAC operation what we are having. And based on this MAC operation, and then ultimately fed to the activation function, and depending upon it, going to get the output. So now what actually are going to do, because we had said neuromorphic computing is going to mimic a biological neuron, which means I need to have these operation of this biological neuron to be transformed in this manner. We have to acquire the signals, and there is a necessity, either I have to enhance the particular stimuli or I have to go for depressing it, then finally it have to be given to the next one. So now when it represents this neuromorphic computing, as a conventional neural network has, we have an input layer, we have output layer, we have some hidden layers. Now, as we speak about the implementation part, generally what we do is, we go for implementing, acquire the weights and bias value, store it somewhere over here, and preferably we go for in-memory computing, we go for multiply. So now, as you can see here, we obtain the spikes, and on obtaining the spikes, depending upon the synapse, we go for transmitting to the next neuron. This is what we are going to do. So when you see about this neuromorphic computing, as I told already, these are the various ICs which are already designed using this neuromorphic. It's not a new one. It's around 2015 itself. They had proved this, for example, with respect to this IBM True North, they had done the classification, image classification for an MNASD data set. They had done the character recognition, they had done it. Okay, so you can see here, if you see about this thing, they had gone for implementing millions of neurons, this much synapses. So basically, the synapse or the neuron is basically mimicking the biological neuron, and it is also going to be a low power chip. So these are the architectures. So now, as I said, this is the neuromorphic computing. These are the chips what has been put forth. Now, as I say about this True North, Lohi, Spine Naked, etc., these are the applications. Maybe for a low power IT, edge AI, for a robotics application, for an autonomous driving ADAS application, for a brain machine interface, for a sensory processing, etc., to go for implementing using this neuromorphic processor. And it's already being proved actually. Now, our question is, what are the things, if I go for neuromorphic computing and if I go for designing a neuromorphic processor, there are certain terminologies what you have to be very much clear so that you are able to derive. So now from the previous information, what we come across is, first step is I have to know about what is this, how this violates. So I have to know what is this, how the neuron is going to be modeled, how the synapse is going to be modeled so that it could be taken to the next level. So these are the two things. So that the entire thing, entire nervous system is something which mimics your neural network actually. So we have to know about certain basics with respect to this neuromorphic computing. Now, when I say about this neuromorphic computing, the first step, what we have to know about is how do we model this spiking neurons? Because now our intention is, I have to go for making this neuromorphic processor to be designed as a chip. So now in the conventional VLSI chip, what we do, we go for RTL design, we write a HTL code, ASIC flow, we complete. That is one approach. Another approach is I go for a custom design. I design a circuit, I go for it. So now the same way, here also when I want to design a neuromorphic processor, there are two approaches again. I can go for an ASIC flow or I can go for a custom. ASIC flow, this is the semi-custom design we could go for, or we can go for the custom design. Whatever may be the type of flow we are doing, the first step is we have to know about what are the things we have to model, which means if I have to emulate, if I have to simulate how my brain is going to function, the primitive thing is I have to model my brain. So when I say about modeling my brain, the primary factor what I have is a neuron. So I have to model the neuron. So when I say about this neuron modeling, there are ample number of mathematical models being put forth by various researchers. Okay, and there are different patterns also being exposed here. For example, the Hodgkin-Huxley model is one model which is replicating your biological neuron. AICTE model is another mathematical model. Integrate and fire model is another model. Like that, lots of spiking neuron models are available. Now, when I say about the spikes, I think all of you can comprehend what is a spike actually. So when you go for this spike, again, there are different types of spikes possible. We have the bursting type, a single spike generated like that, depending upon the type of spike. So the first step is we must be very clear in realizing what type of spike I want to create so that the entire system could be emulated and what is the mathematical model we're going to use. Coming to the second factor, the learning, because whenever we say about any neural network, the learning plays a major role because we have to arrive at the weight value and the bias value so that during the testing phase, the particular weight values and the bias values will be used. Okay, so when I say about the neuromorphic computing learning, as in the conventional neural network, supervised learning, unsupervised reinforcement, all this learning are feasible. But above all this, the unsupervised learning is found to play a huge role in the case of the neuromorphic computing, and especially we have this STDP, spike timing dependent plasticity. So this is one major type of learning we could. Similarly, the type of model what preferably as per the researchers, it is being used is about the integrate and the fire model because this is more, or I can say more exact replica of our conventional brain. Okay, for example, I can say if I'm going to pinch my hand, for a certain time, I'll have the stimuli being transmitted. After that, the pain is being forgotten, right? Similarly, in the case of your integrate fire model, there is an advancement which we call it as a leaky integrate fire model. So what it symbolizes is, after a brief period of time, once a spike is generated, the spike will just automatically lower it down. The spike voltage value will be just going to be lowered, which we call it as a leaky integrate. So this is one area wherein a lot of research is going on, and they had arrived at our brains could be, or neurons could be more modeled exactly in the case of integrate fire, and especially the subset which we call it as a leaky integrate fire. Similarly, the type of learning which will be more suitable for our neuromorphic computing is the STDP, which is basically a Hebbian learning. Even researchers have gone for various other types of learning also, but they have found out this STDP, which we call it as a spike timing dependent plasticity. Okay, because with respect to the time, because we are much bothered about the time the event is generated, and depending upon the generation of the event, how it is going to produce the output. So this STDP technique is going to be much viable while compared with any other type of learning mechanism. Now to go on, the type of how we are going to implement. So now it's something like the conventional method. You can go for a digital custom flow, digital semi-custom flow, or you can go for an analog custom flow. or you can go for a mixed signal platform. Okay. Now, what is this analog? When I say about this analog, I think all of us have worked with the CMOS implementation. So, in the case of the CMOS implementation, because if you have observed, there are three important things what we need to design with the neuromorphic. First one is the neuron implementation. The second one is the synapse, how the weight is carried, that have to be implemented. Then the entire neural network implementation of how the interconnect, etc. So, if I'm able to design my neuron, synapse, which is this, etc., using a CMOS, I call it as a CMOS analog-based neuromorphic computing processor. In the same way, I can go for implementing the same spiking neural network in an ASIC platform or a FPGA platform or using a GPU, etc. So that we call it as a digital flow. And primarily, when you come to the mixed signal, what is mixed signal here is, why we have this mixed signal also in the picture is, as I've been telling you earlier, generally when you want to implement the spiking neural network, initially it will be trained in the conventional platform. The weight values and the bias values will be acquired and stored. Then it will be used in your spiking neural network. So when you go for that sort of scenario, you may have your entire neural network as an analog circuitry, whereas your weight value and bias value could be stored in a memory. And then you could retrieve it. When I say about a memory, again, there are two different aspects. One is you can go for a memory computing, it is more prevalently used, or you can have this as a in a particular VRAM or something, and you can go for acquiring it. So that is what we call it as analog circuitry, digital memory. And the next one we have is a mixed circuitry. And the next one is about the digital. So I think if you work with Cadence, in an HCDM platform, you're able to do that. Okay, you can have a very low coding to be integrated with a of analog circuitry also. So maybe you can have your neuron being deployed, modeled as a CMOS based design or a FinFET based design or whatever, maybe the type of devices, and all the weight values will be acquired in a digital manner. So by writing a very low coding, you'll be able to acquire it. So this is one way. These are the three different ways of how you could go for implementing this neuromorphic architecture. And another aspect of this architecture, what we have to know is about the memory technologies, because now your synapse plays a major role. Whether the particular information, the event has to be taken and given to the next neuron. So that could be done by means of a memory, basically. So now, when you see about this memory, nowadays we have this memristors in picture, right? So when I say about, we'll be learning a little bit about, we're getting to know about that memristors also. So when you're going to use this memristor, this also plays a major role actually. So that is about how the memory technology also plays a role. As I said, it is meant basically with respect to the synaptic plasticity, which means of how the weight value is used or how the strength of connecting to the next neuron is enhanced or depressed. That is about the synaptic plasticity. So this is about the neuromorphic computing architectures. So now there are three things that I had said. One is about the spiking neuron models of what you're going to implement. The second thing is about the type of learning, preferably there's a STDP is preferred. Third thing is how do we implement this? And especially what this point of time I would like to highlight, in most of the cases, they go for analog implementation rather than the semi-custom implementation. Second thing is, even when they're going for an analog implementation, it is preferable to have a memristors because of the property. Because if I go for a CMOS, again I require some memory. So basically the thing is, I have to have a weight value being stored. When I want that weight value to be stored, there are, from our general understanding itself, when I want to store something, I require a memory, right? So when I say about this memory, having a single device which will do the purpose will be a great use. So with respect to that, a memristor is going to be preferred over here. So to say about this SNF is a third generation of artificial neural network, and here we have the discrete spikes to communicate based on the event triggering. And here each neuron is connected by means of the synapse, which is meant for enhancing the signal or depressing the signal accordingly. That is basically the weighted connection between the pair of neurons. When we see about this weighted connection, as a circuit, if you're going to define, there are ample ways, not ample ways I can say. the weight value, what you're going to do, will either enhance or it will depreciate, right? We call it as depression, potentiation or depression. So when I say about the weight value, again, it could be of two types. One could be a binary, one could be a unit, because the weight value, if I'm using a 0 or 1 as a weight, I call it as a binary, right? Again, in certain scenarios, they go for using the weight value to be -1 and 1 also, which means -1, 0, 1. -1 is the depression to the core. I don't want to enhance the signal, I just go for depressing it. So that is another aspect which we call it as how the weight values are being used. Okay, so that is the weighted connection. And basically, the spike timing dependent plasticity is a learning mechanism by which the weight values are being enforced in a spiking neural network. And these spikes are sparse in time. When I mean sparse, it is random, right? Only during that instance of time or during the specific time window, there is a signal being generated. So the main advantage of having an SNN over artificial neural network is here we have very few computing elements and the communication is event-driven. So at this point, I would just like to quote one example over here. I think many of us would have come across a CNN. When I say with the CNN, we have multiple layers of cooling layers. Like that, for the feature extraction, we go for having ample number of layers, which will increase your hardware. But in the case of an SNN, probably another example what I'll be showing you will be able to understand. In the case of an SNN, it's not so. We are having very few computing elements. So basically, with respect to the number of input nodes and the number of output nodes, the computing elements are going to be differing over here. But whereas the general ANN, it's not going to be same. Now, with respect to the big data and all CNN, we are having a huge chunk of hardware being used, which is not in the case of the SNN. And the communication is also event-driven one. So by that, we are not able to, it doesn't make it more power hungry actually. The energy efficiency is also going to be much greater over here. So now, the next aspect, what we are going to look in for a few more minutes is how this is spiking neural network will be implemented. Because we have been speaking with machine learning, with the techniques, and it may be a prediction or a classification or pattern recognition or whatever may be the thing. I'm going to implement as a chip. Okay, so when I go for implementing as a chip, as I said, there are two aspects. One could be the semi-custom flow or it could be the custom flow. Now, I like to confine the things with respect to the custom flow. So the first component, what we need to know about is the neuron models. Okay, because as I said, it's a spike-driven one, it's an event-driven one. So we need to have some models to generate the spikes. So when I say about generating the spikes, how are we going to generate? So in the earlier slide, I told you, here we are having different types of models. And the much prevalent one is called as an integrate and fire. And in that also, we are having various subsets. Okay, the researchers have worked much on this aspect because it is mimicking the biological brain. So based on that, we are having this integrate fire. One such is your axon-killer. The other one is the OTA-based neuron, like that, etc. And we have the another set as the LAF neuron also we will showing you. Now, what is this integrate and fire neuron? Why do we require this? Now, generally, let us assume I'm going for a pattern recognition. Now, when I say about a pattern recognition, it is an image what I'm going to give, which may be from a data set. So, if I'm having a 10 by 10 pixel, let us assume, okay, maybe a 3 by 15 in the case of a EM and AST, etc. Whatever may be the pixel size I'm having, some representation I'm going to have. It is a pixel value. If it is a gray image, it ranges from 0 to 256. Or if it is a binary image, it is a 0 to 1 I'm going to have. So now each and every pixel value has to be given as an event-driven one, which means I have to have that as a spike being given over here. So when that needs to be given as a spike, what actually we are supposed to do is, depending upon the input, I have a pixel value which could be given as a current or which could be given as a voltage. So that must be responsible. Now, when I give to the neuron model, it must be capable of generating that as a spike actually. So I'll just show you that. So now, as you can see here, depending upon my pixel value, it is transformed into a voltage. You can see here, for example, in this 0.5 volts, when I give to this neuron model, it is capable of generating a particular spike. if I'm giving a particular another pixel value, okay, maybe a higher voltage, what we had done is we have gone for an encoding scheme where the pixel value is encoded into the voltage, and similarly it is possible it be encoded as a current value also on an encoding. While I give that, you can see there is a change in the frequency. Okay, so this spike rate will determine what is going to be. So that's what you can see here. These are the different models what we have in what has been realized to implement this neurons. The basic idea behind this is the input will be gathered and we'll have a membrane capacitance. Once that membrane capacitance, depending upon the capacitance value, once the voltage exceeds that particular thing, membrane voltage, automatically it will be given to the particular symmetrical sort of thing, and then based on that it will be accumulated and then it will be given over here. Now, as you can see here, this is a mathematical representation of a LAF neuron. So here, the output of the LAF neuron is going to be 1 if the accumulated membrane voltage is greater than the threshold. Okay, it depends upon how much you're going to have. For example, here, if you see here, this is a Schmidt-based approach, what we are having over here. Now, in this scenario, what happens is, we are giving an input voltage and we are predefined with the particular membrane capacitance. And on charging this, again, we'll have a V membrane being accumulated. So once it exceeds a particular value, when this V membrane it goes beyond a particular value, the Schmidt trigger is triggered, and accordingly, I'm going to get an output over here. So once a spike triggers here, after reaching a particular value, you can see here it will trigger this NMOS gets activated once I get a high value here. So automatically the discharge will happen. So what we can observe here is, at this point of time, only a spike is going to occur. Only when the spike just reaches a particular value, it is going to be discharged. That's why we call it as integrate and fire. Integration happens over here and firing happens. And once the firing happens, it will be discharged over here. And the L stands for the leaky integrate fire. What does this leaky means? Here, we are much bothered about the biological neuron. So as I said, in the real scenario, over a duration of time, the charge gets discharged over here. So we are going to have a leaky transistor over here. So like this, the first step for building a spiking neural network is we have to go for designing a neuron model. So the neuron model could be a CMOS based, or even you can go for a semi-custom approach also. So this is the first aspect. So this is one such output, what you can see here. Now this is basically the encoding had happened. This is when for an MNIST data set, where the encoding had happened and it is being given to the upper as a voltage we're going to feed it over here, and ultimately depending upon that there is a spike rate. So generally when you go for these sort of neuron models, the main emphasis will be on the power, because we expect everything to be very much power efficient. So the first thing is, when you are building a neuron model, maybe with a 180 nanometer technology or a 45 nanometer technology, etc., it must be very much power energy efficient. The second parameter what we have to remember here is about the spike rate. How much spike rate they are able to produce. Okay, so as you can see here, as the voltage increases, the spike rate is also going to be increasing. So accordingly, we are going to have the operation being happening. The entire sequence of operation is processed over here. The third parameter what you have to remember is about the refractory period. What is this refractory period means? For example, once the neuron fires, it will take some more time to process the next input which is coming in. Okay, that brief period of time we call it as a refractory period. So generally we aim all the processing to be much faster. So generally the refractory period we expect it to be much smaller, right? So that the particular neuron will be capable of understanding the next input in an instantaneous manner. So that is about the neuron models. Okay, so this is the first aspect of how the neuron could be modeled. So as I said, it's not only a custom design you have to go for, you can go for a semi-custom design also. But in all these cases, the focus has to be towards the spike rate, the energy efficiency or the power consumption. The third aspect is about the refractory period. Okay, so generally this refractory period will define what is going to be the operating frequency also. Now going on with the second one, because when I say about the neurons, the first one is I have to generate the spikes. That's what we had done in the first scenario. The second aspect is, if the fidelity is good I have to transfer the information to the next neuron, right? Now, our objective is how do I make my neural network to be learning that? Because we all had seen it here. I am having some input being available here. If it is of good fidelity, it has to be transferred, which means I have to have something over here which will either enhance the transmission of signal or it will depress the signal. So the type of learning, as I said, it's an STDP based one. Okay, this the expansion for the STDP is spike timing dependent plasticity. So this is the type of synapse, or in other words, I can say it is a type of implementing the weight over there. Now, the name itself defines it as a spike timing. Now, for example, there are I may be having a input neuron, and according to the inputs what I'm going to provide, I'll be having a post-output neuron also being available over here. So if you consider that, depending upon the time, I have a particular value being stored using a particular memory element, which I call it as the STDP learning. So now, for example, if you see here, I consider two cases. One is your pre-neuron, which I'm going to provide to the first input layer. And the post-synaptic this is what I expect at the output neuron. So if my input neuron is capable of producing a spike before the output neuron, I call it as a long-term potentiation. But certain times, unfortunately, I may be having my output neuron firing fast even before I play, which means I don't want my signal to be transmitted, right? So in that case, what I need to do is I have to go for depreciating the signal strength between one neuron to another. That's we call it as a depression. Okay, so as you can see here, if my presynaptic spike is occurring before the postsynaptic, we call it as long-term potentiation, which means I need to enhance my weight value or I need to enhance my synapse so that the information will be communicated to the next one. But in the case of a long-term depression, I don't want to happen that. I don't want an output to be produced. So what I need to do is the fidelity between these neurons or the synapse must be weakened. That's what we're doing by means of the long-term depression. So if you say about this one, as you can see here, it is a layer one, the presynaptic one, what I'm going to give. And based on that, this postsynaptic. So this is where I'm going to define the weight value. So if I am saying about the weight value versus what is going to be the timing. So depending upon the timing, any two neurons may be undergoing either a long-term potentiation or it could be a long-term depression. So as I said, if the pre-neuron time is ahead of my post-neuron, if the input layer neuron the timing is ahead of my output neuron, I have to enhance the signal, which means I'm going for having an increased weight value. But when I come across a scenario where inadvertently, when an output is going to be firing first, I have to go for depressing the signal. So which means, as you can see here, the weight value is given as a negative value. So this is what we are going to implement. This is what is a learning we are going to have in our spiking neural network. So when I say about this spike timing dependent test, because this is a learning, it's a heavy inverse learning, which I want to incorporate in my circuit, right? So how do I do it? So when I say about this thing, as you can see here, generally the post neuron, the spikes what I'm going to generate, and the pre-neuron spike is also going to be generated. And in the case, generally we use a capacitor. This is a simple way of how the weight value could be enhanced. So generally, if my pre-neuron is coming before my post-neuron, I ensure that the capacitance is charged over here. But in the other case, if my post-neuron spike is coming before my pre-neuron, I ensure that there is no charge accumulated in the capacitance so that the connection will be depressed actually. So now this is the basic principle what we want to implement as a STDP circuit. Now generally, when I say about this STDP, it's not only necessary that I have to go for using some RC value, etc. Nowadays, we are having a non-specific picture which will do the job. As I just go for that, probably then I'll come back to this. So as I said, memory plus resistor. Now we come across many research papers. They would have done the neuron modeling with respect to the CMOS circuitry or FinFET circuitry. But when it comes to the synapse cord, where I have to go for long-term potentiation or depression, they go for using a memristor. So memristor, I think most of it must know, is a memory plus resistor. It's a two-terminal device where it's basically something like the resistance value is maintained equal to that of the synaptic weight actually. So by this way, we are able to save more area because I'm just going to use a single device to do the job. So depending upon the weight, accordingly, I'll be having a resistance being observed over here. So as I said, when we go for these sort of spike timing dependent plasticity, the concept is the same, but the usage could be of different way. Even you can go for a digital implementation also over here. Now, going on, how do we do? So, as I said, these are the various things what you have to know. When you say about STDP, it's a heavy based learning. So, either the connections are strengthened or it's going to be weakened in the case of the long-term depression over here. And here, the timing plays a major role. So, depending upon the timing within the presynaptic and the postsynaptic neuron, we are going to have the weights being enabled or disabled. Then, about the long-term potentiation and the depression of how the weight value varies with respect to the synaptic inputs. Now, going on, how do we implement? So now what we have learned is, we have learned what is a neuron, how do we have the interconnections, but as a neural network, as an entire neural network for doing the job, how do we implement? So basically, there are different ways of how we could do. First one is, we can go for a behavioral modeling. When I say about the behavioral modeling, you can go for the Python implementation, or we have certain frameworks, SpikeNet, etc., where you can go for that sort of modeling also. Another way is you can write a Verilog coding or a VHDL coding, which you can do, or we can go for an ASIC, and then finally we have to go for a fabrication and testing. So when you say about this is one scenario. Another scenario is ultimately we have to go for the 3D stacking when you want to have a dense volume, and generally it is preferable to have a hybrid analog digital both integrated and mixed signal design. So these are the various scenarios, and addition to that, you may be deploying it for a low power array framework also. So when you say about this spiking neural network implementation, how do we? So as I said, these are the basic ways. I think now how actually we are going to do it. So initially itself, I told you. Generally, we go for training the network in a HPC, a high performance computing cluster. And then what we do is we obtain the weight value and the bias value, and we dump it in an ASIC or a custom, whatever, maybe a semi-custom flow or a custom flow. ASIC we go for implementing. So this is the conventional way of how it is implemented so far, because generally we don't intend to go for a training, not to a greater extent. So this is one way of how you could go for a SNM implementation. So this is what I've been telling. You can have a deep neural network domain, which could be a framework, something like a SpikeNet or a Python framework or anything. Then ultimately it could be implemented in this SNN domain. So when I say about implementing the SNN domain, it is something like how the synapse is going to be controlled, whether I want to enhance it, whether I have to go for a long-term potentiation or whether I have to go for depression, etc., and what timing extra. So that is to be transformed. So the main disadvantage what we have is the time taken for retraining, dumping, the procedures involved is going to be much more. The second disadvantage what we have is about when I'm going to transform, lots of transformation in the representation also I have to do. As I said, maybe if it's a point representation, I have to go for quantization, truncation, so that my hardware could be suitable accordingly. So these are the various challenges what it face if I'm going for a DNN implementation followed by a SNN. Now, when I say about the spiking neural network hardware implementation, it could be of aspects. One could be made as a neuromorphic accelerator with several core on-chip, multi-chip configuration. Another is we could focus on the low power aspect also, because if I'm going to aim my neural modeling to be very much power efficient, ultimately as a SNN, I'll be able to arrive at my objective. So these are the two focus of in which your hardware implementation could be. Now, if you say about the spiking neural network, this is one such hardware implementation. Okay, so now what you could see here is, as I had initially told, there are two aspects what you have to know. First is I have to have a spikes being generated using the LAF neuron. So as you can see here, leaky integrate fire neurons are being used over here in the input layer. And this is the output layer where I go for having my output neurons, again, leaky integrate fire. Now, if I'm going to give a pattern, this is meant for a MNIST data set, okay, MNIST, but they had just gone for implementing with few pixels actually. Now, if you see here, it is a 3 by 15, 3 by 5, totally 15 pixel values it's being given over here. Now, depending upon here, they go for the raster scanning, 1 by 1 word. So here, the input LAF neuron is nothing. This is how I'm going to have my input leak integration fire neuron, which is basically comprising a symmetrical configuration here. So on scanning all the 15 pixels, okay, if particularly the value when it is exceeding the membrane voltage, a spike is being generated. Now, if I'm having a 0 here, the first output value had to be 1. This is our objective. I want my output to be 1, the V out to be 1 on identifying a 0. I want my V out to be 6 if it identifies a character 5. So now, this is my input, what I'm going to give. So since there are 15 pixels, I'll be having 15 LAF neurons in the input layer. And since there are 6 possible outputs possible, I'll be having 6 LAF neurons to define each and every output in a significant manner. Now, when I say about this LAF neuron, as I said, we need some learning mechanism here, because initially when I'm giving something, it has to learn, and automatically we are just going to have the during my testing phase, it has to produce. So when you say about this STDP, this is a learning mechanism, a Hebbian learning mechanism, where depending upon my input spike and output spike, this will be either strengthened or it will be depressed. That is what we're going to have. So now we see here, when I want to think, for example, what I do is I go for having my input neuron producing an output neuron producing an output accordingly. For example, if I'm going for training for 0, I ensure that this LAF neuron produces an output 1 and this produces 1. So during this course of time, I have to enhance the signals to this particular V out 1. So what we do here is this STDB has to be, accordingly, it has to be programmed, or this needs to be strengthened over here. So now this type of STDB, what we are having here is this one. So we ensure that the capacitance is being charged only for this case. So all the STDP synapse, okay, we have the charge being stored in the capacitor for learning this 0. Similarly, the second column synapse, what we are having, will be trained for 1, so that during my testing phase, what will happen is accordingly an appropriate voltage will be available through all the STDPs, and once it is accumulated, I'll have an output over here. So this is how the hardware could be implemented. So as I said, if I go for a conventional CNN, I have multiple layers to extract the features and take the decisions accordingly. But here, by just using a crossbar array, this entire architecture we call it as a crossbar array, where depending upon the number of inputs and outputs, I'll be having an array architecture here, which is made of the STDP, which in turn will be giving you the which will be doing the learning, and during the training, automatically the values will be accumulated and it produces an output. Okay. So when you say about this spiking neural network hardware implementation, now here, this is one approach which we call it as a winner take all. So now, on giving an input, for example, if the second column, if everything is fine, I'll get an output only in this V output. So this will signify my V output. That is, it is a character 1. So this is how it is recognized. Now, if you take this sort of a spiking neural network, they are being customized to your particular application. It is basically, it is doing a job of something like relevant to the brain. Only when there is a change in the particular input, that spikes are generated, and because of the spikes, you are going to have that output being obtained over here. So the entire network is going to be occupying a very less area, consuming very less power because of the spike processing alone. And only problem what we have is we have to ensure that we have to go for proper sizing of the transistor. That is nowadays we have various research going on making the entire thing to be operated in a sub-threshold region also. That is also one area venue in which you could go for. So this is about how we could implement a spiking neural network as a custom design. Okay. Similarly, we have lots of semi-custom design approaches also, but now this is a much optimized one. Now I just put through this CMOS implementation. So when I say about this neuromorphic computing, lots of work is going on with integrating with the AI and the ML framework. PyTorch, TensorFlow. These are, and another thing is PyTorch. These are all framework, Python frameworks, which are meant for the SNN implementation. Okay. So what we could do is we can implement the particular SNN, and accordingly we can get to know what type of HTTP, what are the weight values to be stored, etc. And we can go for programming. So this is the future direction. So especially if I have to say, Carnegie Mellon University, they are working on this aspect. And another thing is the spike in deep learning models, because now, as I said, HTTP is a learning model which is more prevalently used. But apart from that, there are lots of research going on in the spiking deep learning models also. In addition to that, they try to ensure a hybrid edge cloud neuromorphic system, and also human-like cognitive architectures are also being in the process. So now, as I said, one more point, because when you say about spiking neural network, this in-memory computing plays a major role here. So apart from the monument architecture, we have all the computing being done on the memory itself. So this will save a lot of space actually. Now, this is a memory store. So now what are the research paradigms? Okay, because now so far what we have been learning is, initially we learned about the difference between the neuromorphic processor while compared to the hardware accelerator. So what are the research paradigms what we are having? In the case of a neuron implementation, as you said, there are ample number of neuron models available. So these are the various neuron models. Now, we thought over this LF neuron, okay, leaky integrate fire, and how this. So here, when we're going for the spiking neuron models, each has its own advantage and disadvantage. As I said, depending upon the pattern, whether it is a bursting type of spikes or a single spike being generated, depending upon the refractory period, each model has its own advantage and disadvantage. But how we are supposed to choose a particular neural model is with respect to the application what we're doing. If it is a pattern recognition, what type of neural model is better? If it is going to be a decision making, what type of neuron? So depending upon the application, you could go for configuring a particular neuron. And apart from that, what is the type of implementation? Whether they go for a digital CMOS or whether it is going to be the analog CMOS or the mixed signal, or how do we go for implementing? Okay, so now with regard to the SNN implementation, these are the various avenues. If we take an ADAS, there is autonomous driving assistance system. We need to know about what is the object. We need some image classification. We need some object detection to know what type of signal is it, whether the vehicle has to take a straight thing or a left turn or a right turn, etc. Or in certain cases, maybe object localization, this image segmentation. This could be coming into picture when you go for some health sector applications. Then action recognition, as I said, prediction or sort of thing. Image generation, prediction also. So these are the research applications where SNNs are being widely used. Now, this is one sector what we had been learning. Now, if you remember, in the initial slides, I was telling about the hardware accelerators, right? Because when you say about the deep learning models, hardware accelerator also plays a major role. So we need to have this MAC architectures also being explored in a wide way. So this is also one such scenario where we go for various type of MAC architectures to enhance the performance. And another thing is about how do we work with the weight values and the bias values. What type of precision we go for, whether we are able to go for a fixed point representation or a floating point. So depending upon that also the MAC architectures are being designed. Maybe dynamic scalability, temporal stability, we go for it. Then how it is being implemented, because certain cases you may be having these weight values and the bias being stored in the memory, retrieving it, all that sort of different ways of implementing also matters over here. So this is about the different research paradigms what we can get to know about when you're working with this sort of neuromorphic computing. Okay, yeah. To say about to summarize the things, initially we started with the need for this neuromorphic computing. And why is so necessary in a machine learning algorithm. And when it comes to deep learning, how your hardware accelerated could play with it. So now when we say about this spiking neural network, there are three important factors what you have to know. One is the neuron, the synapse, and the entire implementation. So the spiking neuron model, as we have seen about the different types, and the synapse, the long-term potentiation, depression, how it's getting affected, etc. And apart from that, how do we prefer implement it? So to conclude with this, when you say about this on-chip AI, it's basically a real-time, energy-efficient, secure intelligence because it overcomes all the drawbacks what we have in terms of cloud computing. Where to be particular about the security breaches, about the latency, all these things, it is getting rid of. That is the main advantage what we have in this on-chip AI. And this is very much crucial for the various autonomous systems and the next generation computing. So since we focus on this on-chip AI, this neuromorphic computing is a best suit for this sort of on-chip AI realization because this is something like brain-inspired computing. So depending upon that, if you're able to come up with a particular prompt hardware, the type of modeling what you want to have for the neurons, the type of training what you want to have, especially as I said, it's about the HTTP mechanism. This neuromorphic computing is greatly mimicking the brain. It's a brain-inspired paradigm. So that this SNN is just behaving as your brain is working. So that all the processing are being done at the edge in a fraction of a second. And in terms of very few femtoseconds, I can say, if I'm working with a 45 nanometer technology itself, I will observe that. And here, the total power consumption when I'm going to deploy it in an edge application is also very minimal. So what I can tell at this point of view is, this is emerging and this is the future of the AI hardware because everywhere you can see there is a need for the intelligence at the edge. It may be your mobile phone or it may be a what I can say microwave or nowadays we are having this automatic what is it, gravy makers, automatic cooking vessels, wherein everywhere to taste to know about the consistency, intelligence comes into picture. So when intelligence comes into picture, and when that is in requirement on the edge, it is always advisable to go for a neuromorphic computing processor as the IBM Logi, the True North, etc. is being put forth by various other companies. Okay, so with this, I would like to conclude my talk. Okay, any queries or any questions if you have, can do for another.
Participants, if you have any queries on today's technical session, please turn on your video and your audio. Kindly, you can clarify with our technical session 9 expert, Dr. Anita Angeline, ma'am, please. Ma'am, already I have posted your contact details in our chat box, including your email, everything. If they have any queries, they will contact you via your email, ma'am.
Sure, sir. Thank you, sir.
So thank you very much, Dr. Anita Angeline, ma'am, for your deeply informative and inspiring session on-chip AI and neuromorphic edge computing. Your lucid explanation of spiking neural networks, memristor-based architecture, and in-memory semiconductor concepts has given our participants profound insights into hardware-driven AI advancement. To deliver the vote of thanks for this session, may I now invite Dr. R. Hemalata, HOD of Biomedical Engineering Department, to address the gathering.
To one and all to gathered here. Thank you very much, Dr. Anita Angeline, ma'am, for your deeply informative and inspiring session on-chip AI, edge computing using neuroformic and in-memory semiconductors. Your lucid explanation of spiking neural networks, memristor-based architecture, and in-memory semiconductors design has provided our participants with profound insights into the emerging trends in hardware-driven artificial intelligence and neuroformic computing. Your discussion on the role of edge AI hardware, low-power neuromorphic chips, and the integration of spiking neuron models into semiconductor systems has beautifully bridged the gap between neuroscience-inspired computing and next-generation hardware technologies. We were truly fascinated by your coverage of real-time edge intelligence, TINI MI, and hybrid cloud edge architectures, which highlighted the future of AI hardware co-designed for IoT and embedded systems. The clarity and the depth with which you presented complex VLSI and neuromorphic concepts made the session both intellectually stimulating and practically insightful. On behalf of the management and Department of Electronics and Communication Engineering, IQSC and IIC of Sri Satyam Engineering College of Technology, we extend our heartfelt gratitude to you, ma'am, for accepting our invitation and delivering such a thought-provoking lecture as a part of our AICTE-sponsored ATAL FTP. Your expertise and passion for advancing on-chip intelligence have truly inspired our faculty participants and researchers to explore the frontiers of in-memory and brain-inspired semiconductor systems. We once again express our sincere appreciation for your valuable time, your engaging presentation, and your warm interaction during the session. Thank you, ma'am.
Thank you,
ma'am.
Professor. Thank you.
Thank you, ma'am. Thank you. So thank you, Dr. Hemlata ma'am, for your kind words, for proposing the vote of thanks so gracefully. Now we move on to technical session 10. So to introduce our distinguished expert for this session, may I now invite Dr. S. Mahendran sir, head of the Department of Electrical and Electronics Engineering, to do the honors.
A pleasant good evening to one and all gathered here. It gives me a great honor to introduce our eminent expert, Dr. D. Dirmal, Associate Dean of Engineering and Technology and Professor in the Department of Electronics and Communication Engineering at Karunya Institute of Technology and Sciences, Coimbatore. Dr. Nirmal is a senior member of IEEE, Fellow of IETE and NAC Assessor for the Government of India. With over 18 years of teaching and research experience, he is widely recognized for his pioneering work in nanoelectronics, gallium nitride technology, device and circuit simulation, sensors, and semiconductor fabrication. He has successfully completed several funded projects from DRDO, ISRO, AICTE, and MAITE with a cumulative grant of over 1.2 crores. His outstanding contributions have earned him prestigious recognitions such as the IETE Srimati Manorama Rathore Memorial Award in the year of 2022, IEI Young Engineers Award in the year 2017, and the Young Scientist Award in the year 2019 from the Academy of Sciences, Chennai. With over 150 plus publications, multiple patents, and numerous keynote addresses at international conferences, Dr. Nirmal sir continues to shape the semiconductor research landscapes in India. We are deeply honored to have such an eminent personality with us to share his expertise on semiconductor fabrication and packaging for smart devices. A session that connects academic innovations with industrial relevance. Sir, we warmly welcome you and look forward to your enlightening session. Thank you very much for the opportunity given to me. Thank you, one and all.
Thank you, sir, for the warm and detailed introduction of our expert. Now, with great pleasure, I invite Dr. D. Nirmal sir to deliver his session on semiconductor fabrication and packaging for smart devices. Sir, the session is yours.
Sir, very good evening.
Good evening, sir. We just introduced your bio by the Dr. S. Mahendran sir, Department of Electrical and Electronics Engineering. You can share your slides and you can start your presentation, sir, please.
Yeah, thank you. Thank you. Good evening, all of you. It's my pleasure and honor to be there with you today evening for this ATAL faculty development program. The next 1 hour, which we are going to discuss on the electronic system design and manufacturing. Before going to my presentation, I just want to get some feedback from all of you. Can you share your information there in the chat box about which area you are working? Probably I just wanted to get some feedback from few audience so that I can slightly orient my presentation towards that. Can I get some feedback from which area you are working there in your research domain? Probably VLSI design, device modeling, or can I get some feedback from the audience to the chat box? I hope audience are there.
Yes, sir. Yes, sir.
Yeah. Okay, cadence, somebody. Okay, good. All right. VLSI design. Good. Okay. Low power. Okay. All right. Few more. I just want to get, apart from this domain, anybody is there? Probably any computer science based faculties are there, or to try to understand so that I can bridge a little bit. Okay. So there are a couple of faculties out there. Okay. Thank you. Thanks for your response. Now I'll move to my presentation slide. So electronic system design and manufacturing is the key and the buzzword for current trend now. If you look at the scenario there in the semiconductor mission, okay, I just wanted to start with some facts and figures so that we can clearly understand where the manufacturing sectors is moving ahead and what is the next step for us in this direction, right? If you look at the current market there in India, I have not compared with the global market. What is our market? The electronic production currently contribute actually 3.4% of our economy. Okay, our total economy, the electronic production contributes 3.4%. That will grow to $320 billion by 2026. That is a prediction. Yes, rapidly we are moving. Which additionally measures potential to reach actually $410 billion. Okay. No, it will be around 6.2%. So our prediction, we are going to meet $7.3 trillion business. That is the focus which we have based on these. Okay, market what is available there for electronics. So electronics market is a very, very key and the vital role for the GDP growth of our country. So only there is a lot of emphasis on semiconductor manufacturing there, in all the areas from the industries to the academic institutions as well as for the startup. Everywhere people talks about semiconductors, semiconductor manufacturing, design, verification, testing. All these factors are coming into the picture. Now look at that. Now a boost in ESDM will again result in massive capacity of the job sectors. Okay, if you could check that now, there could be an alternate for the IT industry. There is a one source is actually electronic system design and manufacturing sector. Okay, there is a huge potential and the market available. One is for the country growth and the second one is for the human resource development there. Okay, because we actually 1.4 trillion billion people are there. So we need to understand this capacity. We need to have a clear job role for all the engineers. So there is a need. We need to fulfill that requirement. The ESDM is a key factor. Now currently 50%, okay, our electronic products are imported. Okay, this is very, very important point to be noted. And by total demand, it reaches $368 billion. The import is going to get reduced. Okay, that is what we are predicting. Okay, with all the efforts we are taking, the import is going to be reduced. Now, if the import is going to get reduced, then the ecosystem which we are trying to develop in a semiconductor mission or semiconductor focus, that will definitely yield market demand. So from these 3 points, you can clearly understand where we stand there in the market, how our GDP is going to focus on it. Well, I'm not saying only semiconductor mission is going to impact much on the GDP. All other factors, our space, our defense corridors, our agriculture, products and other things. Because even for our space, our electronic products are very, very key. When you go for our defense sector, okay, the defense developments, our semiconductor sectors are very, very keen. Even for agriculture, smart irrigation or robotics or artificial intelligence based, we talk about LLM and SLM, all these things. Actually, these market plays very, very important and vital role. Okay, so far we relied on all the imports. Now time has come. If you completely rely on our imports, we will miss actually a major components there, or major a share or the revenue things to the other country. So keeping this in our mind only, we have moved forward to the next operation. Okay, there are few areas, okay, this ESDM sectors is covering. One is electronic material market. Okay, I just give all the markets first, and I'll give what it's all about. This impact there for your architectural design. Okay, one is material, another is a component. There is a huge market there for component. The third one is a design. Okay, system development is one area where we work on it. We are talking about quantum computing, quantum communication, quantum sensing, and quantum materials. Okay, this all comes under system development. Okay. Then we have a verification market. Clear verification market is available. Then the manufacturing sector, there are manufacturing sectors, then the possibility of the manufacturing sectors are there. Then, of course, we have some service in the electronics as well. Okay. So these are some of the major areas where these electronic markets are coming into a vital role. Okay. Well, first is a material engineering. Ask me, what makes much impact there for the manufacturing sectors for material engineering? Okay, without material engineering or the novelty there in the material engineering, the energy concept which we are talking currently. When we talk about any of the system design, we say about the power consumption, your speed of the devices, and also the complexity of the circuits. Okay, majorly we talks about the power and the area. Okay, energy minimization and the power utilization must be minimum. That is the requirement for all the system design. If you look at the energy sectors there in our country, if you go in this space, because all our cloud systems are consuming a lot of energy for our operations. We extensively use the LLMs for our system developments. And if you take all the IT sectors also mainly uses on the ChatGPT or DeepSeek or such kind of modules for using your LLM, it consumes actually huge amount of power from the cloud. Okay, we may sometimes realize because it's coming from large databases. Okay, we have to really understand the importance of the energy it is used for any process. Okay, it is not only the system development, but by in all the means what we use is there for our day-to-day life, it consumes huge amount of energy. Okay, this is actually a major issue or major problem we are going to face there in the future. So only we keep on says, minimum utilization of energy in all the sectors. Okay. So keeping that, all our systems need to be go with the minimum amount of energy. Okay, this is the requirement. If we come to the material sectors, okay, we earlier worked with the bulk materials. Okay, very big materials. Then we moved to a micron structures. Then we moved to a nano-based material, then now the quantum-based materials. Okay, so this is evolution from the bulk to the nanoscale to the quantum materials. It has actually huge market into it. When you work on the silicon is its own property for their semiconductors, because it's based on its melting point and the energy. It has certain energy to use for it. Okay, but when we are going to find the alternate for the silicon, there are other materials from 3,5 compounds. Also, materials are available. We can replace the silicon with the indium, or you can replace with germanium, such kind of a materials. So the efficiency of the system is going to get improved, but how far the energy consumption of the devices, this is very, very critical in stage. Okay. We need to have the wider visibility or the speeder operation, but at the same time, the energy consumption should be lesser. So there is a trade-off. Whether we need to go with a efficient system or whether we need to work on your power consumption reduction. Okay. So the material engineering has a very, very key important role in it. Okay. Now people talking about the single compound material to the dual compound material and the composite materials. Okay. There is a different compounds of materials we add and make the functionality there for our systems. Okay. Then the second is a component. Okay, component market, as you all aware, from the materials we build on the basic components, your PN diode or your transistors. Okay, these are all some of the fundamental devices which is present there for all your systems. As all the VLSI design engineers knows about the Moore's law. If you ask me a question that Moore's law now its existence, okay, there are some applications we cannot replace the Moore's law. There are applications where we need to radically change and move to the tunneling devices for our operation. Okay. So the component is one of the factor where I will detailedly discuss in the coming slide. You will understand. Then the design of the circuits, we use Cadence extensively for it. We use Synopsys extensively for it. We use ADS for bridging with, okay, all the tools which we use it, and also the verification part. Okay. A lot of universal verification tools are available, then the manufacturing and the services. This is what actually evolution of your electronic system from materials to the devices. I want to touch on the semiconductor devices extensively today rather than on the circuits, because when you work on your energy consumptions there in the device level, we can save our energy extensively there in the architecture. Because this is the building block for the architecture. Okay? The electronic devices is the building block for the architectural building. When we are going to make an optimization solution there in the device itself. Okay. So the utilization there, when you go for the billions and trillions of transistors there in the architecture, the power consumption used by the architecture is going to be unlimited, reduced. Okay. That is what earlier we started with the bipolar junction transistors and the MOSFET. Okay, you all are aware about it. So we are very much clear on the bipolar junction transistors and MOSFETs. Okay, once we moved to the metal oxide semiconductor technology, there we found the technological changes. Okay, from the nanometer, probably I will touch a little bit later. Okay. From there, what we understand when we move from one technology node to another technology node, there is a short channel effect. To overcome the short channel effect, we have gone for the different dimensions of that. Okay, that comes your FinFET. Then we gone for nanowire and nanosheet, IRDS, and fabrication and fabless technology. These are all the portions which I am going to discuss clearly. Okay, this is an international technology roadmap for semiconductors. Earlier, we used to follow that. You may ask me now, sir, why you are sharing this to you, to make you to understand very clearly about the technology node, how it has progressed. If I ask you a question, what is the technology node currently India is using there for our fabrication unit? Okay. Can anyone say what is the technology node we are using there in India for our fabrication purpose? From audience, some answers in some technology node with some nanometers. Some random answers, probably anybody can. Now you can open your mic and you can share. I hope my question is clear to all of you. See, there are technology nodes involved there in the system. Okay, what is the current technology node which India is having this. Okay, we are having commercial technology node. I am giving a clue that we have ACL Chandigarh. There is a unit from ministry. What is the technology node we do there currently? I hope all are listening.
Yes, sir. We are listening, sir.
Okay. Thank you. So what I am trying to say is you take from material engineering to the devices. The devices consist of P material and the N material, so it forms a diode. Now, back-to-back diode, it forms actually your transistors. Then your transistors move to MOS transistors. The MOS transistors gate length defines the technology. As you all aware, the MOS transistors gate length defines the technology, LG, okay? Length of the gate. If the length of the gate is 180 nanometer, we say it is a 180 nanometer technology. Earlier, it was micron technology. Okay, all Intel, IBM, Qualcomm, Broadcom, NXP, okay, or Infineon, all the major players of semiconductors all followed this technology nodes. Okay, just like that, they cannot change the technology node. There's a standard consortium we had. It's an international technology roadmap for semiconductors. They have given the roadmap for us. Okay, from this technology node to this technology node, this is the time period we have to shift it and do it. All right. 180 nanometer was the matured one. Actually, everybody has followed. From there, we have from micron to 180, then 180 nanometer to 90 nanometer, 90 nanometer to 65, 65 to 45, 45 to 32, 22, 14, 10, less than 10, 5. Okay, this is a technology node stringing. Yeah. You all know about the applications of the technology node stringing. Because of that only, we could able to make the compact mobile phone architectures. Laptops become very compact. All your board systems become compact because the size of the transistors has been reduced. This is a major breakthrough which we have done there in the semiconductor industry. Okay, we should understand this, right? When you look at the transistor size is 180 nanometer, that's become very bulky in nature. Okay. But currently, the world is now working towards less than 5 nanometer technology. Okay. Less than 5 nanometer technology for the applications, day-to-day applications of architectures, which we are using is that. I'll come back to my question. The question which I have asked you is, what is the technology node we have used for in our country? In our country, the technology node currently the ACL Chandigarh uses is 180 nanometer. We are planning to build, actually all the approvals are done for 45 nanometer. Now you may ask me a question, sir, world now they are moving from 10 nanometer and less than 10 nanometer. What is the necessity for us to work on 180 nanometer? I will answer your question if you ask me a question like that. See, there are applications, still the matured node, we need to work on it. When you go for the matured node, there are a few advantages. One is cost. Okay, the cost of the module or the block, which is going to be lesser. Why? Because we need to go for less than 10 nanometer technology. We should have such a lithography machine to do the process, and the operational cost is going to be very much higher. Okay, we need to handle the operation cost of the device is going to be very much higher. When you are going for the operational cost or the fabrication cost of that, it's going to be higher. The automatically your architectural cost is going to become very high. Okay, this is the reason we still hold on the technology where some applications. So, for example, for IoT applications, I doesn't want to talk about the miniaturizations because it's going to have a communication systems. In that cases, okay, 180 nanometer is more than enough for me to do it. Okay, all right. I doesn't require that. If some applications require that less in the node, then we need to work towards it. So there are huge opportunities there in 180 nanometer itself. Okay, when you go for some of the surgeries, robotic surgeries with some architecture with lower technology node is sufficient for. No, we doesn't want to go with the deep lower. Okay, so this is a very important concept. All of you should understand. One challenge which we had there is when you reduce from 180 nanometer to less than 180 nanometer 90 and 60, the length is going to be stringed. If the length is going to be stringed, the electrons can quickly tunnel from one source to the other source. Okay, this is one of the challenges which you have faced there in the MOS. Now we are celebrating the FET 100. Okay, field effect transistors 100th year we are celebrating there in the whole world. Okay, the IEEE community and electron device community is celebrating that in the whole world. Okay, see what we are saying is the patent which we have got. Okay, the patent which we have got, it has given a larger breakthrough there in the market. Okay. Now you change from your dimensions to 180 to 90. The electron can quickly tunnel. Because of that, okay, the controllability issue is coming to the picture. To address the controllability issue, we have gone from the single gate transistors to the double gate transistors. Okay, instead of going for single gate, the double gate transistors. See, this all these diagrams will tell you very clearly about what are the different structures of this, because the transistor structures, when you talk about it, actually is a huge. Okay, for our seminar today, probably I am limiting to some of the core important points, and I'll move to the next topic. All right. So when we talk about this issue, the single gate to double gate, we have moved. Okay. Then also we try to find out whether can you able to have the better controllability of the electron between source to the drain. So it's not able to control. So the horizontal current flow, we could not able to make it, because you are vertically applying the field and trying to control the horizontal current flow. No, it's quite difficult for us, because the field distributions and other effects are playing a huge role there in the channel. So what we have done, when we have moved to the tri-gate structures, instead of double gate, we have moved to the tri-gate structure to have it. But the advantage of the tri-gate structures, we could be able to control the electron between source to the drain. But the disadvantage is the fabrication complexity. Okay, the fabrication complexity is very, very huge. So we could not be able to manage with that. But still, some of the architectures are following the tri-gate technology. Okay, tri-gate architectures. When you go and buy some architectures, they will ask what technology node you are following. Okay, you can easily figure out, okay, this is the technology. If the technology node is going to be stringed there in your architecture, automatically the cost of the architecture is going to be higher, or cost of the processor is going to be higher. Okay, this is thumb rule normally we have there in the semiconductor system, because when we touch on these architecture, that means when you touch on these devices, when you put it to the circuit design, to the module and the system, automatically you have optimized energy level. Now, for an example, you take a case study. Okay, you are using 180 nanometer. 180 nanometer if you are using, and the area is going to be bulky. If the area is higher, automatically you have a higher resistance there. Okay, no, the current flow will be lesser. Then you calculate the power. Definitely, the power utilization is going to be higher only. To address that, we are going for lesser, nodes. Okay, lesser node. When you are going to use, build an architecture using 180 nanometer for, billions of transistors and using for your architecture. Now another guy is using, 5 nanometer technology node device and building an architecture. If you compare the power utilization of that, it's a huge difference. Okay, it's a huge difference. So only we are trying to understand and rectifying that problem there in the technology node. This is very, very important. Okay, this is very, very important for the semiconductor system design. Okay, so the industries are addressing that issue, and they are moving from one technology node to another technology. Don't forget that always we are keeping the higher node also there in the process for various other applications, who is looking forward some low cost devices. But you are going, this is a trade-off. Okay, you are going to concentrate on the cost of the system, or you are going to work on the power consumption of the system. The long run, if we look at electronic system, the factor power utilization became a major challenge there. Okay, so people are trying to move from one system to another system. I hope you all are very clear with the technology node, because if you are not understanding about this, when you go for semiconductor system design, okay, when the large side we will use for clock gating techniques, architectural designs, okay, multi-threading, all these techniques we can use it there in the architectural and the device level and the circuit level. But we are not touched on the device level, your energy. Okay, that's become very challenge there in the semiconductor system, right? So I request all of you to explore these images. These images I have showed already. No, 90 nanometer, 65, 45, 32, 22, and less than that. Now we look at that from the tri-gate structure. We have moved to the quad gate to the nanowire to the nanosheet transistors. Currently, we are working with the nanosheet transistors and the fork sheet transistors. Okay, I'll show you some of the architectures here. Okay, from this slide, you can see now we are talking about the multi-stack of architectures. Okay, not only one device on the lateral, we are looking forward vertical kind of a structure so that we can easily address the issues of covering more number of transistors there in a single waveform. Okay. There are other places where the metals, okay, when you go for multi-layer stacking of the devices, when you look at this, 2024, 27, and 2030, it's talking about actually multi-layers, okay, multi-layers of the devices. When you are going for a multi-layers of the devices, the metallization techniques need to be checked. When you talk about metallization, there you are, a trench and via is going to play a vital role there, because your alignment of the trench and via, okay, the metals, that is again a crucial part for the designs. Okay, when these things are worked out and the functionality is clear, only then we can go for a circuit design using this. Okay, but looks the transistors, we see that's just a very simple device. But when you take it to the architectural level, the functionality of the transistors, then the operation of the transistors, and the power utilization of the transistors, when you calculate, that becomes a very huge. There comes the semiconductor device design is very much important and popular there for all the semiconductor industries. Okay, right. So then we have I just wanted to cover a few points related to this. Is I've taken from the applied materials for your understanding, from the planar to a vertical transistors. Okay, you may ask me why we want to move from the planar to vertical transistors. If you have a planar transistors, the wafer will be filled with your full coverage of the area. We are talking about the area minimization. Now, how should we address this problem? When you are going to address this problem, we need to move from the planar to the vertical structures. The vertical structures gives you a better visibility again. All right, you can stack more number of transistors. Okay, you can have a multi-layers of transistors. You can have your optimized design there in the left. Okay, there you have gate-all-around structures. We have built it on it. Okay, 3-5 compounds FinFETs. Okay, this is very important. Okay, I told about the material engineering, silica. Silicon is the functionally readily available material for all the operation. Now, if you check for new material components are coming to the picture like 3-5 compounds. Okay, the gallium, indium, those kind of material, indium phosphates. Okay, these are all very popular materials. Now the industries are working. Okay, there are two classes you can think about it for the semiconductor on the whole. Okay, one is your low power design, another one is the high power design. Low power, so far I'm talking about the low power structures, okay, low power devices or all the architectures what we develop. On the other hand, we need to have a very precision with high frequency applications. High frequency applications, we need to work for the gigahertz to terahertz of operations. For space, we talks about we are a space power, okay. We want to build our own space technologies, okay. We have to have a semiconductor modules built by us in high frequency of operations. Okay, we develop for 20 gigahertz, 200 gigahertz, up to we works with some of the terahertz of operations. Look at our defense system. Okay, we talks about stealth technology. In the stealth, actually, this high frequency components plays very vital role. Okay, in these components, we are not going to talk about the power. Okay, only the efficiency. The so far what I discussed is entirely a different vertical where we talks about the dimensions is very crucial. But we come to the high power devices, the dimensions, of course, the dimensions are crucial. But what we see is we want to have a higher breakdown voltage. See, withstanding capability of the device, the voltage should be sometime around the 1000 volt or 2000 volt or 2500 volt. Okay, and also we need to operate on the cryogenic, temperature. Okay, this is actually a two different vertical where the semiconductor devices are developed. Okay, so all of you be very clear on these concepts, because on the general, people talks about semiconductor devices are low power. Okay, but based on your applications, on the requirement for the architectural building, okay, we will say actually, VLSI. Okay, VLSI is your low power structure. When you go for MMICs, okay, microwave monolithic integrated circuits, we need to talk about the high frequency and high power application for the communication system. That also comes under actually semiconductor technology. Okay, see, our SEL Chandigarh, we have different verticals. One's with the low power structures, and the other team will work on the high power structure. And another one field is also available. So OIC, okay, optoelectronic integrated circuits. There always we talks about emission of light. Okay, how to make the communication through the light. Okay, that's what our quantum missions is, a quantum communication, how we are going to use the light transmission data. Okay, there is also actually semiconductor devices and materials are involved to make a emission and receiving the signal. I hope you all are getting my point very clearly. Okay, because these are all some of the important areas where our manufacturing, our semiconductor technologies are moving. All right, you have a low power system, you have a high power systems. We need to work on with your optoelectronic integrated circuits, but the material engineering is common for all. The silicon you can do with silicon for low, high, as well as optoelectronic system. You want to build with 3-5 components materials for your low, high, and optical systems, we can build on it. Okay, our lasers are built with indium gallium arsenide, okay, composites materials, okay, gallium arsenide composite material. A lot of composites are used for all the verticals. All right. These are all about the design aspects. Okay. Yes, somebody asked something.
No, sir, you can continue, sir.
Okay. Thank you. So now I'm showing from coming back to again to the low power stuff. Okay, this is the latest of FinFET structure people are using. Okay, from there to a nanosheet. The second one is a nanosheet. Now fork sheet transistors have emerged. There are C-type transistors available for the architectures. Okay, these devices are used to have a higher efficiency there in the system and better computing capability and also lesser power utilization. Okay, this is the tricky where this lower technology nodes coming to the picture. Right. I would like to say this is a world first 2 nanometer nano chip produced by IBM. There are a lot of players available. I've just taken an example for you to understand how we move further in this direction. Okay. Now I wanted to take you to a benchmarking of this. Okay. So this is fine. Okay. How we need to benchmark our work. Okay. Earlier we used to follow the ITRS. Now we are following IRDS, International Roadmap for Devices and Systems. Okay. We earlier talks about only the material to devices. Okay, that there is a standard node we have given for the fabrication industries to follow it. Now, as a system development, how we are going to make the system development by looking at the current scenario there in the market, it's very rapidly changing, very rapid. When we talk about some system development today, probably the next 3 months, it may available there in the market or may not be available there in the market. When such a dynamic systems we have now. We look at the application side there in the computing, okay, computing side. Now AI has completely taken over. Almost it's done. Okay, no more people are giving a feedback that all our AI systems are generating the code what is required for us. Okay. So no more people wanted to build the code. Already everything is available by the system. Okay, AI has given, because it works with a large set of databases and taking and giving an optimized solution for it. Okay, whether our system is ready to compute that. All right. No, whether system, our system, what we have developed, can you able to compute that is very, very important to understand. Okay, for that, this roadmap, okay, this roadmap will help you very clearly. Okay, what need to be followed, how it need to be followed, what is the updation which is present there. I request all of you to have a quick review on this. After the session, if somebody working on your areas, you can have a look on this IRDS. You'll get actually a lot of databases, what is available there in it. Okay, there people talks about Moore's law, okay, that is low, and the high power systems, okay, analog systems, power systems, sensors, actuators, and biochips, and so on and so forth. Because we should have a clear benchmark for the applications what we do. Okay, sensors and actuators are very, very important for any of the system development. Okay, when you talk about the bioengineering, okay, genomic sequencing, all right, these are all things are coming there. When you put that and doing as a system, okay, system, it is not all the things. When you take all the bio systems, it is all electronic system. Biomolecules we take, and our device will verify the markers and give the results for it. Okay, simple, small sensors. But when you come to full-fledged biosystems, we should know, okay, what need to be taken, okay, what kind of materials need to be used for the biological component. When you are going for when you are going to inhale something, it should not make some harmful to our body. Okay, such kind of selection procedures of the materials also very, very important. Okay, in this juncture, I wanted to tell you about the materials. The materials which we are using currently is a solid material. Okay, what we are trying to do there is a flexible material. A lot of flexible materials are there in the market currently. Okay, now we are trying to move from the flexible to the biodegradable materials, because all our electronic systems are not biodegradable in nature. Okay, what we use is it is not biodegradable in nature. All right. If it is going to be biodegradable material or not, we need to identify and check. Okay, this is very, very important. In this stage, right? These are all some of the materials I just wanted to cover it with you. Or recent advancement in semiconductor material, high power gallium nitride. Our team is extensively working on the gallium nitride material. Okay, gallium nitride material, and also the graphene based materials are there. Okay, these are some of the materials where market is much required to work on the system development. Okay, these are some of the areas where ITRS is giving semiconductor technology can move into different areas. Okay, you take any of the areas. Okay, all the system developments is works on these areas. Okay, there are benchmarks for us. Okay, IRDS is giving a benchmark. You take agriculture. Okay, agriculture is a smart agriculture. We are talking about it. The smart agriculture we are talking about is using the drone system. Okay, the autonomous drones. How we are going to build the autonomous drones? Okay, autonomous drones has a lot of operations into it. Okay, now it is going to be there in very high end now from here onwards. Now, what we predict is now currently the mobile shops we have in all the places like this. In the future, a lot of drone shops will be there. Okay, for various applications. Okay, because of the electronic developments, now every houses may have a drone. People used to take the drone for their applications, for various applications. Now itself, in many developed countries started using the drones for their day-to-day life affairs. Okay, so our cost of living also is going to get reduced because of this kind of a development. All right. Then the healthcare sector is wide. Okay, you can name all the robotic operations happening there. Okay, I am living there in Coimbatore. In many of the hospitals, they used to do the robotic surgery here. Okay, that is very common nowadays. Okay, people are able to use the robotic system for it. It's basically an electronic system which drive with no sensors and the actuators. Okay, because this is very, very crucial. There are some standardization we need to work, and the communications. There should not be any delay there in the communications when you do such kind of operations, right? Then you talk about gaming, finance, data security, social media, automotive systems, okay, entertainment, robotics I have told, okay, all the areas which has an applications for the semiconductors. Why semiconductor technology is booming, or why there are a lot of emphasis on the semiconductor technology? Because of the vast applications in these areas. It's not only the electronic system which we develop and do it. Okay, a specific ASIC has been developed. It is for particular applications, and the IP is developed by our end. Okay, the IP is holded for us. Then it makes automatically a good startup to make actually a good revenue model out of it. That is what actually we are trying to do there from the semiconductor mission. Okay, I just covered this. Okay, this is some of the areas where we should work on it with the wearable technologies and the smartphone, medical, autonomous vehicle is coming in a very big way based on the architecture currently developed for our systems. Okay, these are the points which I just want to move it. Okay? I want to tell you very important concepts here about the fabrication of the semiconductors. Okay, before going to the fabrications, the design is very, very important. Why design is very, very important for the devices and systems? When we do some fabrication of electronic devices or a system, when we go for testing of that system, if the failure, if it is occurred there in the fabricated devices, then we will lose actually huge amount of money in the process. To avoid that, primarily we go for the system design. You get the requirement from the customer, okay, and build, you write your requirements. Based on the requirement, we go for the device design. Okay, this is the first step. When the design is done, then we will validate the designs with the mathematical models. Okay, this is the process flow involved in it. Once the mathematical model and the semiconductor design is carried out perfectly, okay, then the validation is completed. Then the file, okay, given for the fabrication unit. Okay. There's a fabrication unit consumes, okay, a huge amount of equipments as well as the huge amount of running cost. You take fabrication equipment, the industries has, okay, there are different classes of the fabrication unit. If you look at this image, this is one of the images it's taken from the internet, okay, for your understanding. Now, there are different classes of fabrication units are available. Okay, we have different classes. The class 1 is the highest purity fabrication unit, okay, where you have all the pure form of devices and the system development will happen. When you go for the highest level of the class operation, the cost of the production of particular devices or system is going to be higher. Okay, this is the reason. Okay, we cannot afford to waste our money and time into the defect systems. So only people go for the design and simulation of the devices first. This is very, very important for the semiconductors, because we doesn't want to lose any of the resources or any of the wealth into this process. Okay, so defect should be minimum. Okay, from the wafer stage to the devices, circuits, each level we have a testing. That is what the verification is very, very crucial there for the electronic system. In the bare metal, that is your bare wafer has a defects. Okay, if the die, using that die, if you make a circuit, and if using that die, if you are bringing to the architecture, okay, definitely their architecture is going to be end up in a failure. Okay, sometimes they says that there is a failure there in the system. Okay, they say there is a module failure. So we are reverting back that model from the market. would have heard about the news, okay? Because the failure, if it is occurred and it is not found there in the beginning stage or subsequent stage of the production, okay, the end, when you make a system and the system is getting toggled there, okay, the entire process is a failure one. So only very, very precise operations will taken there in the clean room technology. Okay, we cannot afford any of the defects there in the wafers and the dies. Okay, if the yield of the wafer is very much higher, then the process is very good. Okay, the yield is going to be lesser. Okay, the die. Okay, the how many dies we are going to make it is lesser, then we will not get the best there in the outcome. Right. So what I request all of you to keep. Okay, when each step of the fabrication is very important. Before going for the fabrication, the design is very, very important. So the design, simulation, and validation of the semiconductor design, okay, semiconductor systems or devices are very, very crucial. There are tools we use to do it. Okay, technological CAD. Some of you may be working on that tools. Okay, we use Cadence, Synopsys, or Atlas TCAD for it. Okay, these are the major tools. Okay, people are working in this. If you say Global Foundries works with both the tools. Okay, what they get the customer requirement, and they will design the devices, or based on the devices, they go for a circuit designs and then fabrication, then they deliver the product to the customers. Okay, that is a flow which all the semiconductor industries are following. All right, with the existing IP what they have. Okay, I'm underlining that word because there is IPs are very, very important. These are some of the equipments I wanted to share it to you, so that you'll understand how effective and the cost consumed. Okay, see, in our university we work with some of the equipments like pulse laser deposition, some of the sputtering and some of the solar cell testing facilities are available. Probably what we do is there in our university, we do a complete setup of design simulation, and we do have metal coating and also oxide coating equipments. For some stacks we can do. Then the testing facility is also available. So IV characteristics and the power characteristics we can verify. It's actually a small scale of design on verifications. But largely, mainly what we do is we do some projects for the government of India. We work with ISRO, we work with the DRDO and some of the international universities where, see, the requirement is the design. Okay, they want a perfect design. Because once the design is perfectly done, they have an equipment to fabricate, okay, the process to implement. Okay, sometimes the industries will give us a similar requirement to different players. Okay, the industry, how it works, the industry give this is the requirement for me and give it to different players. Okay, different players will design it and give the design to them. Once the design is delivered, they will validate it. Okay, the perfect design will go for the fabrication of the process. All right. So I wanted to highlight some of the industries working in the semicon. Okay. The key point is actually all the semiconductor industries are trying to build the IP for the intellectual property rights. I request all the faculty members also present here. When we wanted to grow in the semiconductor field from our nation to grow, okay, we should have actually IP for us. Okay, when we have IP for us, whether it is a soft core IP or hard core IP, okay, we should have our own IP. If we have our own IP, then the revenue which I've told about there in the first slide, okay, we are talking about the $7.5 trillion. This is the focus. Okay, we are moving towards the Vikshit Bharat. Okay, such kind of focus. So we should build on our own IPs. Okay, whether our applications focus, 2 nanometer technology is required for my application, we have to validate. If it is yes, based on that, we need to work for it. No, if it is not required for my application, I'm going to develop some IoT application. This 2 nanometer is not required. See, I'll go with lesser technology. No. Then we need to go for that specific. Okay, that specific, that module, that then you have to go for the IP development. Once your IP is developed, then we can challenge with this industries. Okay, the suggestion would be you can work with the industries and jointly develop an IP if possible, so that the validation become easy and the commercialization also become quite easy. There are huge opportunities. You look at that, okay, Qualcomm, Xilinx, Nvidia, okay, major players are there. Okay, Huawei is there. Okay, see, many. Okay, it's only a small unit I have given. Okay, Infineon is doing very good there in the high power systems. Okay, or the autonomous vehicle system, EV vehicle systems, the system developments. Okay, NXP is doing well. Okay, so these are the industries where we have a lot of people. I wanted to thank the Ministry of Information Technology, Department of Space, and Ministry of Defense for taking our works. Okay, we have contributed few of the system design works for these labs. Okay, what we have done is the design is carried out and we have delivered the design to them for the fabrications, for the launches, as well as for the applications to be get developed in the systems. All right, these are all some of the areas where you can work on it for the semiconductor manufacturing sectors. As you all aware, you are completely aware about the semiconductor manufacturing mission now. Okay, so there is a process happening for the wafers. Wafer is a one area we primarily now started producing on it. Now we are moving from the wafers to the circuit there in the higher technology nodes. We could able to deliver the ICs for that. Okay, for based on applications. Now the key, in which market we are going to capture the IC for what. Okay, this is the key factor which we need to address in this. Okay, that's all from my end for today's session. I would like to take a few questions if you have, because these kind of sessions will definitely give an insight to all of you and get to know if you have some kind of questions from your end. I know it's over to the organizers. I would like to get a few questions from the audience so that I can very well answer for. So, yeah. You'd like to share?
Participants, if you have any queries on technical session 10, please clarify with your queries with our expert, please.
No, you
via
want
chat box or unmute your audio and ask your queries.
Yeah, please. This is very important session. Now, probably you can ask questions. So you can ask on technology, nodes, materials, factors, power factors, or any of the research opportunities, or product development, okay, and incubation aspects. Okay, any possible ways you can ask. Probably we can ready to help you out.
Professor Annamalai sir, do you have any queries, please? No. 30 minutes, we have it more, please.
See, I purposely kept that time because we should have a lot of question and discussion, because then only we can deliver what best we can give it to the faculty members, those who are pursuing your research or some kind of collaborations. Sir, hopefully my session is clear to all of you, right? So I was just thinking about it. All right, it is clear to all. I hope the participants are there, because that is very important.
Yes, sir, I will share your contact details along with your email ID via chat box and WhatsApp group for any queries if they ask in future via both.
Yeah, no. If there are no questions, probably
now,
I want
here, please clarify your doubts with our today's expert, Dr. Nirmal sir.
Good evening, sir.
Yeah, good evening. Thank you.
Sir, could you please explain about the incubation process? How to?
Okay. So I am taking little brief on incubation. When you talk about specifically on the semiconductor systems, first we should have a clear market study before going for any kind of incubation process. It is not only for semiconductors, for any means. Okay. Clear market study is much required. How do you do market study? We have to take the US market. We need to take the market of European Union, that side. Then Asia Pacific, then your Latin America, that region. Okay, these are the major areas. Okay, UK, these areas we need to have a market share. For example, I am going to build one, what to say, one IC, a small circuit. Okay, small circuit, which is going to deliver for 5 watt. Okay, this is the requirement. Okay, for I'm just giving one small example. Okay, 5 watt. I need to find out where and all these circuits are used. Okay, these circuits are used for all the continents or not. First, this is the very important. Okay, if the circuits are used in US, Europe, and Asian countries, then we have a clear market for it. Now, what is the problem for incubation? People are developing a products, okay, but that products are viable for market. Okay, the question is, is it viable for market or not? It's a greater challenge. We have huge products developed, but we could not able to market it. Okay, because of the lack of the analysis or study of the market. Okay, the first step is a market study. Whenever you start some work, we should have a market. How do you do the market study? No, you have to have a different industries to connect it. So for example, you are going to work on semiconductors, we have to list all the first top 10 companies. Okay, that first 10 companies and your area. Okay, this is the area which I am going to work on it. What are the patents these companies or IPs, what these companies have produced? Okay, it is not from the journals. From the journals, we can take some kind of ideas. Okay, the main is the IPs. Okay, we have to identify the IPs. Then what we should do is we need to go for IP to the data sheets. Okay, see, we have to get, for example, Cree is giving some data sheet for your product. We should first emulate that product based on the Cree. Okay, the data sheet and the IP. If you have IP and the data sheet with you, probably we can come to a common place where this is what actually the current market, they are working on it. Okay, from there, what are the challenges they would have observed it? Okay, we have to explore on literature. You can connect it with the industry for that. So for example, you are working for this module for competitor for the Infineon. We have to try to connect with the Infineon and have a discussions. Then you come up with some kind of solution for that. Then you start working on it, make a product. Then you go for your pre-incubation process and the incubation process. Then automatically it will flourish. Okay, this back work. Okay, what is the requirement for your product to be incubated? Okay, this is very important. Okay, when you have that requirement ready, then your incubation will go hand. Otherwise, no, we will start. See, most of the time, the examples are, we are starting 100 startups. Okay, the percentage of survival of the startups are very limited, but we are good. Okay, in one hand, we are good. We are having a lot of startups in India. Some of the startups are very successful in nature, but some startups we could not able to have a successful because of the lack of market study. Okay, the market study is much required. So when you go before going for a product development to incubate, we should have a clear market study. Okay, now one suggestion would be, try to involve the industry also into your market study. try to involve some of the premier universities from India and abroad. If you could able to identify the team, okay, and fix it, then your incubation will have a perfect growth. Okay, we can easily nurture the incubation of your process. I hope I have answered your question to you.
Thank you, sir.
Yeah.
Two more faculty members have posted their queries on the chat box, sir. Please, you can see that.
Memory elements with CNT fed with the CMOS circuit. Shall I design the memory elements with carbon nanotubes? See, carbon nanotubes, you can design it. Okay, no doubt about it. But check the stability. Okay, stability factor is very, very important when you go for carbon nanotube for the CMOS design. See, there are a lot of CNTs available, okay, for the memory applications already there in the market. But my question, whether is there any novelty there in your CNT itself? You have a novelty there in the CNT, then you can plan for the CMOS design. Your already available market CNT are going to do it. I will not recommend in this stage, because there are a lot of developments already happened there in carbon nanotubes. Okay, but if you have a new process synthesis with lesser cost or some kind of a novelty there in the structure of the CNT, then probably you can do it. Or else, I will not recommend us to straight away go with your simulation tool for the design. Okay, that is my view. It may be differed from somebody else as well. I hope I have answered my question. Then,
Good evening, sir.
yeah, thank you.
Sir, in the semiconductor field, so while we are submitting a proposal for funding,
Okay.
so what are all the steps we need to be considered, like publications and all? So your views, sir.
Yeah, thank you, sir, for your question. When you talk about publications, there are different categories of your projects. Okay, your projects comes under one. Normally we talk about international projects, and we go with the national projects. When we are talking about international projects, definitely you should have a collaborations with the international team. Okay, unless and until we don't have a collaboration with the international team, international project submission is not going to make much impact. So sometimes people submit a project, just they communicate with some professor or somebody and they'll submit it. The success of the project is very, very limited. The basic step is we should have some collaboration of publications. So any project, national project, if you're going for a national project on the semiconductor core field, minimum we should have 2 SCA publications as a core. For me, I should have minimum 2 publications in the same field. For example, I'm going to submit it on carbon nanotube based some of the CMOS design. For example, okay, I should have minimum 2 publications in this my name. Then you have weightage on it. You are going to submit some project to DRDO or ISR. They'll be asking your top 2 publications. That's it. All right. When you go for DST, then your all the publications will be scaled there in the data. Your H index also plays a role. Always try to give the relevant publications for your projects. Okay, number of publications is not going for me, for my observations and experiences concerned. Okay, number of publications doesn't matter there. You should have the quality of your publications. That's a key for your project fetching. Then your deliverables. Okay, deliverables must be there towards IP. Okay, all project agencies are for IP development. Your IP, your process of IP is not defined there in the outcome, or at least the thought process is not given towards an IP. The sanctioning of the projects is quite difficult. Okay, either we should have our product development to the IP, or at least a soft core, soft IPs. Something is much required to get into it. Okay, and also relevance to the nation. Okay, this is also very, very important. What are a nation's relevance in the world? Okay? If it is aligned towards the nation's relevance as well as your sustainable development goals, okay, this matching also much required when you go for the projects. Okay? Your objectives must be very clearly spelled out with 2 or 3 objectives. Okay, your outcomes also be aligned with that, with the national relevance of the national mission and with the sustainable goals. Okay, the revenue model, if possible, some of the study based on market analysis. Okay, market analysis. Earlier we used to say it's a literature survey and other things. Now people talking about the market survey. Okay, what is there in the market currently? How we are going to change, or how what is the novelty we are going to inject there based on the market requirement. Okay, such kind of things, if you put it there in the proposals, probably you will get a chances of getting the projects good. Now always try to match benchmark with the peers with that who is working in this area, in the hardcore area. Then try to match with the universities, international universities as well. This is one request to all of you. Connect with the international universities where your relevant areas. Okay, it may be initially it may be a little difficult to connect, but over the period we can easily connect it and focus and work towards it. I hope I have answered your questions, sir.
Yes, sir. Yes, I clearly understood. Thank you, sir.
Thank you.
One more faculty have posted their queries in the chat box, sir. Suresh Kumar.
Could you please recommend books or materials for students to encourage? Sir, for me, now arrays, you wanted to study books. I cannot say straight away what is a book and other things. I always recommend to go with some prestigious journals as a first step, and the second step should be your IPs. Okay, your patents. Okay, the patent you have to identify. Systolic array. What is the recent patent? Then we can go with some of the products developed based on this array. Okay, there comes you will get actually a depth of stuff. Okay, you wanted to understand some basics. Probably you can think about some of the textbooks, but I would suggest in this way. You have a larger picture already. You decided is a systolic array. Okay, a systolic array you have decided already. Then you straight away you can go for a patent search. Okay, systolic array patent search, and you can find. Then it is quite easy for you to converge. Otherwise, many times PhD scholars or somebody comes with some good thoughts. When they say it's a 3 months work or 6 months work. When I go for a patent search, probably would have been done already for quite long. They say novelty is missing. When they submit some publications and other things, they'll get, okay, there is no novelty there in the paper, because it's already worked out stuff. So I could suggest in this way, but you can check for some of the handbooks, or that will help you. Okay, handbooks may help you because it's compiled from different authors. Okay, that is one way you can. I hope I have. This is all my experience towards how do you do literature and connect it and do it. So you optimize. Now we have to use extensively this LLMs to reduce our time as well. Okay. I hope I have done. Yeah, thank you. Magnetic channel junction is also more useful in designing memory elements. Yes, magnetic channel junction is very popular now for the semiconductor device. You could be able to make some junctions, and you could be able to control the magnetic parameters. That's a very good scope available for it, because it's based on the spinning. Okay. So that is a good point to take, but I'm not working on magnetic tunneling junction, so I'm not the right person to comment on it. But there are few colleagues I know, they are working in this area. there are a lot of scopes available, but provided the spin and the integration of the magnetic circuit to the coupling. Okay, coupling is very much a standalone magnetics people are doing. When you are going to couple your magnetic circuit to some other, that integration part is a key. There are a lot of challenges people are getting. Probably you can keep that also in your mind for the process. I hope so. Thank you. All right. So, any other questions? Hopefully, I have addressed some of your queries which you have asked. There is a very.
Sir, have you answered for one more question from Annamalai sir? Max?
Yeah, I have answered right now, sir. Right now, I have answered. Okay. So what I'm doing is I'm typing my email ID. All right. This is my email ID, and this is my email. All two emails I have sent it. If you have any questions related to this, probably you can write to me. I can very well answer within the scope of where we are working. Suppose you want to get some fabrication connections or some of the equipments or some of the tools utilizations. So I must thank Government of India in this. Actually, Chip to Startup program has given a lot of emphasis to many of the institutions. Now people can use all the tools. Okay, you can make use of the tools. But the next step, we need to plan for the next step to how to implement and take the tape out of it and give it to the market. Okay, that bridge actually we need to do it. Many of the people are trying to do. Probably in those lines, if you are having some suggestions or help, probably you can write to me. I can very well support you in this direction. So is there any questions there? Probably I can answer, or else probably, sir,
Yes,
wind
sir.
up the session.
Yes, sir. Right. So thank you very much, Dr. D. Nirmal sir, for your understanding and thoughtful provoking session on semiconductor fabrication and packaging for smart devices. Your discussion on IRDS technology, fabrication standards, nanosheet fetch evaluation, and India's emerging semiconductor manufacturing ecosystem has been truly inspiring and insightful. To deliver the vote of thanks for this session, may I now invite Professor M. Prisita Arthi, Head of the Department of Artificial Intelligence and Data Science, to deliver the formal thanks.
Good evening, sir. Thank you very much, Dr. D. Nirmal, for your outstanding and thought-provoking session on semiconductor fabrication and packaging for smart devices. Your in-depth discussion on International Roadmap for Devices and System, IRDS, fabrication technology standards, and evolution of nanosheet and FinFET structures provided our participants with a comprehensive understanding of present and futures of semiconductors manufacturing. Your presentations on India's emerging electronic system design and manufacturing (ESDM) ecosystem, the potential for the large-scale job creation, and the nation's growing capacity in the chip fabrication and packaging has been truly inspiring. The way you connect academic research and industrial applications and policy-level initiatives highlighted a holistic perspective of how semiconductor innovations can drive the national growth. We were particularly impressed by your insights on the device scaling challenges beyond Moore's law, advancement in nanowire and nanosheet FET technologies, and strategic role of AI integration in semiconductor system. Your real-world example from IRDS technology trends, clean room fabrication environments, and industrial collaboration models offered our participant valuable direction for future R&D pursuits. On behalf of Sri Satyam College of Engineering and Technology, the Department of Electronics and Communication Engineering, and the ATAL FDP Organizing Committee, we extend our heartfelt gratitude to you, sir, for graciously accepting our invitation and sharing your expertise in this high-impact domain. Your session has truly ignited enthusiasm among our participants to explore deeper research and innovation in semiconductor device engineering, fabrication process automation, and smart system integration. We sincerely thank you once again, sir, for your valuable contribution, your engaging delivery, and your inspiring presence in today's session. Thank you, sir.
So thank you, madam, for your thoughtful vote of thanks and for concluding the session gracefully. With this, we have successfully concluded day 5 of our ATAL FDP on semiconductor for smart system applications in IoT, AI, and next generation devices. We extend our heartfelt thanks to our eminent experts, Dr. A. Anita Angelin and Dr. D. Nirmal sir, for sharing their valuable knowledge and expertise. Our sincere gratitude also goes to the heads of the department, Professor C. Sasikumar sir, Dr. R. Hemalata madam, Dr. S. Mahendran sir, and Professor M. Prista Arti ma'am for their graceful introductions and vote of thanks. Special appreciation to the organizing team, coordinators, technical support members, and all our enthusiastic participants for their continued involvement. We look forward to seeing you all again tomorrow for day 6, the concluding day of our FDP. Thank you all and have a pleasant evening.
Thank you, sir. All the very best. Thank you so much.
Sir. Thank you so much,
you.
sir.
Sir, please tell me the time for tomorrow's session, sir.
Yes, sir. Sir, for tomorrow, the session will be started at 2. First of all, I want to tell how many sessions, technical section we have on tomorrow. 3 technical sessions, 1 online and feedback session, and validatory function. The technical session will be started at 2 p.m. to 3:30 for technical session 11. For technical session 12, it will be started from 3:30 to 5. Then 5 to 6:30, technical session 13. Once we complete our technical session 13, you will have the online test from 6:30 to 7:30. Finally, we will have the validatory function or validatory session 7:30 to 8:30. 7:30 to 8. That's it. We will share all the details to our WhatsApp group. Once we complete our today's this session, technical session 10, I will share tomorrow agendas along with all the details, test details, everything via our WhatsApp group.
So this link will be open only for 1 hour, sir.
Yes, sir. Examination 6:30 to 7:30, 1 hour.
Sir, for 1 hour open means so many troubles will be occur, sir.
Yes, sir. We will give the sufficient time to complete the test, sir. You don't worry.
Thank you, sir.
Okay. Other participants, if you want any clarifications regarding today's session as well as tomorrow's sessions, please. Okay. Ma'am, shall we wind up the session, ma'am?
Okay, sir. Yes, yes, sir. Yes.
Okay. Thank you, ma'am.